All right. Hello, good morning. We are going to start. And so I'm just supposed to welcome you this morning. And as you know, in the classroom, as I said, this is more like a school for you as students. And as students, I always that you are the future. In 4 or 5 years, the amount of the available So the whole concept is to give you all the knowledge you need. And then as a people, to push the agenda of having to put Ghana and Africa on this path of quantum science and technology. So this has been organized for you. But in the education or in the format that I always know, you cannot attend a school without a certificate. So that's what you need to show that with the student that you are in this. So as I told you, there will be those strict measures of having to be taking attendance to dictate your presence here, so that at the end you can also get a certificate as well. And so I'll not like to belabor the point. I'll just fix it our heads since the facilitator is ready. We are very, very fortunate to have experienced and well-renowned professors here across the globe. And today is no one but Professor Tommaso Calambo. And I believe you've all seen his profile. And so he's here, and then he's going to take you on the quantum optimal. So please really take time, study, ask questions, and be sure of what you're studying. Thank you very much, Thomas.
Thank you very much. So I think this is the first lecture in this school. So, well, I will give some introduction about a few aspects, how you build a quantum computer, and then how you make it work. And I would like to know how many people here are from physics and how many from computer science. So if you are from physics, can you raise your hand? Excellent. And if you are from computer science, can you raise your hand? Okay. And any other fields here? Okay, which fields? May I ask? Mathematics? Mathematics. Material science? Okay, very good. Okay, so we have not only physicists here, so I will not go into many detailed formulas. I want to give an idea what it means to build a quantum computer and make it function, and which kind of software we use. And this goes into two directions, of course. One direction, we are using optimal control, which is a form of machine learning, this kind of reinforcement learning. Because you try to achieve a goal, and then you try, it doesn't work, you have to help improve that. So this is one direction of interaction between machine learning and quantum computing. And then my colleague here will give a lecture in the next days on the other direction, how you can use a quantum computer to improve machine learning. So there is this interaction in both directions. So it is relevant both for physicists, mathematicians, and computer scientists of various kinds, including bioinformatics. And what I want to do is today to just deal with how we use machine learning, reinforcement learning in particular, to make sure that we make better devices. I will define what I mean by that. I'm a theoretical physicist, so I do not build these machines myself, but I am sort of helping other people to do that. So the first slide that I have actually is from my colleague Yasser Omar, who was supposed to be teaching at this school, and he asked me to relay this slide because unfortunately he was in Accra at the UNESCO conference, in which also Professor Martin was, and actually he got food poisoning, so he could not travel. And he asked me to show you this slide in the beginning about his Portuguese Quantum Institute. He's from Portugal, and he's a quantum institute which is doing initiatives in education, training, and also working with 5 African countries. He has a quantum education lab, which develops pedagogical kits, which are low cost and broad access. And also they do research on quantum algorithms, quantum internet, and quantum sensors. And also they have they are able to sort of help support setting up labs in photonics and cold atoms, really starting from scratch. Also, he has been working very strongly in supporting the World Quantum Day and also the International Year of Quantum Science and Technology. You see here a map of all the events that took place last year with the World Quantum Day, which is April 14th. Okay, so just this was just because Yasser is not able to be here, and now I will start telling you a little bit about the quantum stack. So we call a quantum stack similar to what in classical computer science we call a computing stack. And of course, the purpose is that we want to run some algorithms. We want to solve some problems and calculate something, compute something on our computers. But in order to have these algorithms, of course, you start from some program, some code. You have to compile that into instructions which the machine can perform. So here is where I'm going to focus most. Okay, firmware. So the software which takes the assembly language, if you wish, for a quantum computer, a sequence of quantum gates, and tries to make them as well as possible, because of course there are problems in quantum computers which are different than classical computers for making the hardware work. So this is the whole stack, and there could be, each one of these points would deserve an entire university course, but what I'm going to focus on is this aspect of firmware or control of the hardware. So we often hear that when we want to build a quantum computer, we need to be able to have scalability, to scale up the size of this quantum computer to a very large number of qubits. Otherwise, we will not be able to use it for something useful. At the moment, quantum computers are not able to do anything useful because they are too small. The quantum computers that we have are up to maybe a couple of hundred qubits, and there is elementary error correction to fix the errors which come up, show up in this computation, but we need many thousands of these, and maybe even more of these error-corrected qubits, which means that we expect that we need hundreds of thousands, if not millions, of physical qubits. So there is a large gap from what we can do now, only a few hundred qubits, and those many that we need to have a quantum computer which can solve useful problems. Yeah, for instance, quantum machine learning, as will be the lecture in the next days. So, and I'm asking here the question, what do we need physically to be able to do that? Okay, so how do we look? A quantum processor is something which takes some qubits, quantum bits. There will also be a lecture specifically by Leonardo Guidoni, I think, defining in detail what qubits are. Okay, qubits are quantum bits. For our purpose here, we can just say that they are quantum systems, like bits are two-level systems. So physical systems which can take two possible levels, 0 and 1, two possible states. Also, quantum bits have two possible states. The point is that they obey the laws of quantum mechanics. So it means that I can write a superposition. These quantum bits can be at the same time in different states. For instance, if I have two quantum bits, I will have all the four possible combinations 0, 0, 0, 1, 1, 0, and 1, 1, and a general state of this system, psi, will be written as a superposition. So of all of this with the different complex amplitudes. And for those of you who may not be familiar with quantum mechanics, this will be explained more in detail in the lecture by Leonardo Guidoni. What matters here for this lecture is that once I have a string of these qubits, so the initial state here is, a combination of zeros and ones, and many combinations of zeros and ones summed upon each other, so in a superposition, then what we want to do is to manipulate them with our quantum machine. And this quantum machine has to perform a transformation so that we get an output that hopefully will contain the solution to the problem that we are studying. And this output needs to be, this is the important point, the initial state, the input, transformed with this unitary transformation. It means a quantum transformation which will preserve the superposition between the different states. Only if we are able to do that, then we will be able to realize quantum algorithms which can be useful. So the point is, how do we do that? And in fact, if we look inside this box, one would think, okay, the box I showed before is a general transformation of n qubits, which takes them in another state of n qubits. But there is one important advantage here if we want to build this box, that we can decompose it in smaller boxes, in smaller units, which are single qubit gates and 2 qubit gates. It turns out that I can realize any generic unitary transformation, any n qubit transformation, just by composing transformation on individual qubits and on 2 qubits. I don't even need to do 3 qubit transformations. It will still work. I just have to compose them in the proper way. So these kind of gates are, again, quantum transformation, unitary transformations, which means that they have to preserve this superposition. If I start in 0 and 1, the output will be what would be the output of 0 plus what would be the output of 1. So that's the linearity of quantum mechanics. And this is for single qubit gates. And for 2 qubit gates, I just need to be able to do one specific type of 2 qubit gate. In this case, it's a control knot. Control knot means that I have a certain truth table, like in classical computing, so that I have some input combination of input states, and each of those is transformed into an output state in such a way that if the first qubit, the qubit A, which we call the control qubit, which acts on the target qubit, if the control qubit is in state 0, you see that the target qubit remains in the same state that it was in the beginning. So the control qubit acts as a switch. If the switch is in 0, nothing happens. But when I switch on the control node, because my control qubit is in 1, then what I get is that it's a control knot. So the second qubit gets flipped from 0 to 1 or from 1 to 0, according to what is actually a knot operation. And of course, this would be a truth table of a classical gate, which could do this transformation. The point about doing it with a quantum computer is that if I have a superposition, a coherent superposition, a sum with different complex amplitudes of these input states, I will get the sum of the corresponding output states. That's the difficulty of achieving that, and we're going to see a little bit how we can do that. So indeed, one example, actually at the moment, the most advanced platform for quantum computing is with neutral atoms. When we say platforms with quantum computers, we mean that actually it's not like classical stuff. Okay, so the computers that we wonderful.
Can we go back to this?
Yes.
So, they say that we need
because if that's the real trick. So this is the theorem of universality of quantum computing, because even if I would have to do a 3 qubit transformation, a general one, I tell you, here is a 3 qubit gate that I would like to do, and you have to realize it. You will always be able to decompose it in a sequence of single qubit gates and 2 qubit gates. And you will never need to do more than that. Even more, I need to be able to do any single qubit gate, but I just need one specific type of 2 qubit gate, which is universal, the control knot. It could be also something else, okay? But I just need to be able to do one specific type of 2 qubit gate, and together with any single qubit gates, I can reproduce any 3 qubit, 4 qubit, n qubit transformation. So in the end, I do not need to do that, because this would be more complicated. Imagine if I would have to, for every time, I have like 2 atoms, and then I juggle them in a way to get a 2 qubit gate. But then I have 3, and then I have to start over again. And then when I have 4, no, but this is not necessary, because once I know how to do my 2 qubit gate and any single qubit gate, I can do everything else I want. Does this answer your question? Excellent. Do we have other questions? So my favorite question, I should have. So when I give a course in my university, I have announced a prize, which no one has ever won. Okay. The prize is, well, now I'm not sure if it's a prize or a punishment. The prize would be a free lunch in the mensa with the professor. Okay. Now, is it a punishment? Is it a prize? I'm not sure. However, nobody ever won it. And the prize is for the first person who manages to ask a stupid question. Students over many years have tried hard to ask stupid questions. They have always failed. Okay. So my guess is that we will always fail. But if anybody manages to ask a stupid question, you will be invited for lunch. And remember, my favorite question, as I always tell the students, is, I have not understood that, can you please repeat? Okay, this is a very useful question, it is my favorite, because if anyone asks that, they are sure that there is several other people which are going to take advantage of the same question. So please do that, and I love being interrupted with your hand raised. So let's try to do that. Let's see if we get a stupid question. Okay. Oh yes. Oh wonderful. Yes, please. Sorry. Yes, the 3 qubits. The question from your colleague. Yes. Yes. So it is not, let's say, to be more precise, it is not necessary. Okay. So in some very specific case, if in some system it comes out that it is very easy and straightforward to do multiple qubit transformation, sometimes exceptionally we may decide to use it, but in general this is not necessary. So essentially it really means that we can stop worrying about 3, 4, n qubit transformations, because of course in the end what we want to do, our goal is to do an n qubit transformation, but we will never have to realize physically, okay, more than 2 qubits. That's a very powerful result, which is the theorem of universality of quantum computing. And the set of control nodes, for instance, so it could be another one, control phases, another gate, and single qubit gates is called a universal set because it enables to exactly do that. So thanks a lot. Okay, so you are the first one who failed to ask us questions. Thank you very much for that. Now, when we want to make this, okay, we have different platforms. As I mentioned before, with our standard computers, which we all have in front of us, this is based on silicon. Okay, so the way in which you do bits is there are silicon chips, there are transistors which are miniaturized and so on and so on. But we don't have an analogous to that. We don't have like silicon for quantum computing. Okay, so we just have different possibilities. Actually, it's also possible to have silicon qubits for quantum computing, but this is not very advanced. The most advanced platforms are superconducting qubits, such as IBM and Google, for instance, are working on. Ion qubits, such as Quantinuum, the company from which our colleague is coming. I would say at the moment, Quantinuum is the world's most advanced company with ion trap quantum computing. It pains me to say it because I am European and they are American, but that's the fact. You know, what can we do? So we have to scientifically go on with the data, and they are the most advanced. So that's very remarkable what they can do. But even more advanced in the sense, objectively, in the sense of the number of qubits that you can use at the moment, is neutral atoms. Okay. So there are a few companies, in particular one again in the US, Square, but also a couple in Europe, which are able to manipulate a couple hundred qubits coherently, and even to create some logical qubits and make logical operations. So how does this work? In atoms, you have internal states which are electronic states. Okay. For those of you who are not physicists, you know, and maybe computer scientists, or you know, in chemistry in school, we learn that there are different, you know, orbitals S, P, D, and so on and so forth for our atoms, and electrons can jump between one and the other. So the states 0 and 1 will be 2 of these electronic states. And then I can couple them with some laser fields. The details are not important here, but the point is, if I illuminate some atom with some laser fields, since laser is quantum light, so it is coherent, I can move the electron from one state to the other, but also I can keep it in between. I can create a superposition of those states. So this is what enables me to use atoms as quantum leaps. And then, of course, I need to, when I say I illuminate my atoms with laser, of course, if I want to do a single qubit operation on a certain qubit, I must be able to just address the laser onto that qubit. which means I must be able to trap my atoms. I must be able to cool them down to a low vibrational state so that they are in the zero energy quantum state, the almost zero energy quantum state, because as we know, there is no such thing as complete vacuum in quantum mechanics. But so we keep the atoms as still as possible. We have to address them with laser fields, and then we are going to be able to. Oh, it doesn't work. So what's the problem? Oh, what do you mean? Can you hear me? But they could hear me also before. But what was the Zoom is not hearing us. Okay, very good. Okay, so what I was saying is that, and this is what they can do in this also in the continuum, what they can do, they have ions, so they are charged atoms. So it means that they need to have lasers which can be focused to illuminate just one individual atom or ion at a time. So that's how we can build those specific quantum gates, which we can use to make those n-qubit transformations. So, and this was for single qubit operations. Now let's consider how we can do 2-qubit operations, which amounts to entangling atoms, to creating quantum correlations, which then have no classical analog and are actually the reason why a quantum computer can be more powerful than a classical computer. So here I am giving one example of how you can create that entanglement. I'm giving this example because I will take it again over and over when I explain how do we use quantum control to actually make the best possible quantum gates. This is not as much as atoms are not the only possible platform for quantum computing, as we said, but also this particular collisional gates is not the only possible way to do quantum operations. Actually, what they are using at the moment is more interactions between dipoles in Rydberg excited atoms, but this becomes very technical. Instead, this one can be visualized very easily. How do we understand this? So I have my atoms here, and each of them can be in a superposition of 0 and 1, as we said before. And we have to imagine that time is flowing upwards, okay? So my atoms start here, and they are localized, and each of them is in some superposition 0 and 1. And now I move these atoms in a state-dependent way. So I will have a force on the atoms, which depends on the qubit state. If it is in 0, for instance, no force. Those are the red lines. If my atom is in the state 1, then it will be moved around. Or I could also move an atom here from 0 to the left, and then bring it to close to another in state 1. So if I can realize this state-dependent force, which I can also do with lasers, because lasers can exert forces on atoms, and lasers can be coupled in a different way to different electronic states. So I can have a state-dependent force, and then I can move the atoms around depending on their internal state. So in the end, I can realize something which is of this kind. My atoms will have some sort of interaction between them, but also with ions. So what I'm saying here is a scheme which works both with atoms and ions. As we know, ions, they are charged. So charges of the same sign repel each other. So if I bring two ions closer, then their energy will be raised, okay, because I need to push them to stay closer because they want to stay apart. If I take them more apart, the energy will go down. So it means that I can change the energy of my atoms 2 by 2 in a way which is dependent on the internal state, because I can move them depending on the internal state. So what it means is that I have an energy shift, a change in energy, and this is a Hamiltonian, so a quantum function which tells us what, or rather operator, which tells us how much is the energy and how to deal with it in a quantum way. And the effect of this, that if I switch on, I turn on and off an energy shift, I will get a quantum phase, which is attached to my state. This is a concept which may be a little bit exotic for non-physicists. So I'm just mentioning, in other words, that by moving the atoms in a way which is dependent on the state, I can get a logical operation. Why? Because this phase here is, which will be a minus sign at some point, okay, will be dependent on the internal states. So some like 0, 0, 0, 1, and 1, 0 components of my wave function of my quantum state will not get that phase, but the 1, 1 component will be flipped, will get a minus sign. And in this way, I can get entanglement, I can get correlation, which I can use for those logical operations. In fact, one can show that this operation here is equivalent to the control knot that we discussed before. So if I am able to do this physical operation, moving the atoms around and controlling their energy, then I can build my logical gates, I can build my n-qubit transformations, I can make a quantum computer. And now the point is, I want to do this with the best possible quality. I don't want to make mistakes. I don't want to have errors there. And here are the criteria which I have to fulfill. If I want to build a quantum processor, those are called the Vincenzo criteria. David Vincenzo is a colleague of mine in Forschung Zentrum Jülich in Germany. And when he was working at IBM 25 years ago, he published a paper saying what are the criteria which a quantum computer has to fulfill. The first one we already addressed is scalability. I have to be able to make many qubits and make them work in a quantum way. Another criterion is I have to be able to put them in some initial state, like a good initial 0 state. Then I have the problem of decoherence, because, well, of course, also classical bits, they have errors. In our classical computers and cell phones, there is error correction, which is running in the background, as this is something which the computer scientists know very well, and the physicists less, or they are less used to that. But the computer scientists, they know that I have error correction. So every time passes, I am checking periodically whether some bits are flipped, because I am encoding bits with more logical bits, with more physical bits. And there are processes so that I can retrieve the correct state. But in quantum, this is more difficult, because in quantum, what we have the problem of decoherence, which means that, a qubit, the person who invented the word qubit, Ben Schumacher, said once, keeping a qubit coherent is much more difficult than keeping a snowball, solid in the middle of hell. Okay, already having a snowball in the middle of Africa is a pretty tough job. Okay, it will melt very quickly. But then you take it in the middle of hell, and it will melt instantly, and the qubit is much worse. Okay, so because there are very short coherence times in which the quantum properties are preserved before the interaction with the environment destroys them. And so we have to have coherence times as long as possible. Then we need to be able, during the coherence on a time scale which is shorter than that, we have to be quick, because before my qubit melts down, I have to be able to do my logical operations. So this is the universal set of gates that I was mentioning before. And then I have to be able to read out the state. Then there are other criteria for quantum communication, but we're not focusing on those here at the moment. So our goal is to satisfy these requirements here. And actually, nobody knows yet how to do it fully with really full scalability. Actually, tonight I am flying back to Europe, and on Tuesday I have a workshop which I will be coordinating in Brussels, in which we bring people, scientists from all member states and industry, and even the governments together to see how we can now attack this problem and create a fault-tolerant quantum computer in Europe. Okay, so this is really a problem which is taking place now. And what I am showing is how do we build some building blocks for attacking that. So it means that if I want to scale up the number of qubits, I have some wishes. I want a quantum register with many qubits, and I want this decoherence that I discussed before to be very low. Also, I want to do many quantum gates before the qubits are decohered. So I want fast gate operations, as fast as possible, but also I cannot do them too fast because I want them to be fast but precise. Okay? Because I want high fidelity, I want low errors in order to indeed do my whole quantum computation in a way which then brings me to the result. And if I look at how to make these things with ultra-cold atoms, for instance, or ions, what I need to do, experimentally, I need to isolate and manipulate very precisely those atoms and ions one by one. And then, typically, this can be done in some lattice potential or in some periodic structure in which I can have a lattice of this. So here is an example of an optical lattice. So a potential which is created, a force for atoms, which is trapping atoms in a regular array due to interfering laser beams. The interference pattern, so laser beams come from electromagnetic and very coherent radiation, which has a very precise spatial frequency. And if I superimpose two of those, I get an interference pattern, which will have maxima and minima, and around the minima, I can trap my atoms. So I could also have, because as we said before, lasers are coupled in different ways to different internal states, different electronic states of atoms, I can have in this way those potentials which can be moved, in a state-dependent way. So let's say, like before, red was the 0 state and 1 is the 1 state. I am moving the potential only from the 1 state, and if I go back and forth, you see that whenever a left atom in 1 state meets a right atom in 0 state, there is a collision, there is an energy, and this will enable me to create that phase which has a logical value, which can make sure I have then a 2-qubit gate. So that's the way in which I can realize physically a quantum computer with those neutral atoms. So the point is, so a little bit more in detail, okay, here is, as I said before, there are interfering lasers, and these potentials can be different for different internal states. And we can move the different potentials because they have different polarizations. So you can have a laser which is circularly polarized. And there is a question. Thank you. Thank you, because yes, I was not looking in the proper direction. Yes. Maybe you want to ask in the mic so that I guess also people on Zoom will hear. Yes.
For the previous slide, when you are discussing the stellarities,
Yes.
the gates. Except one way for it to be scalable is to have fast equations.
Yes.
So with the gates, how do you increase the speed of the equation? How very fast?
Okay, the question was, how do you increase the speed of operation? So you must know that in life, there are 3 types of questions. There are good questions, excellent questions, and wonderful questions. A good question is something where I don't know the answer. I say, oh, that's a good question. Then an excellent question is something where I know the answer. And a wonderful question is something which I am going to give the answer in the next slides. So yours is an excellent question. Sorry, a wonderful question. Because my point actually is precisely how do I use this machine learning, this reinforcement learning, to make gates faster and more precise. And actually, we are going even to see, I don't know if there is enough time, okay? But at the end of my presentation, I have also something about the quantum speed limit. So really the maximum speed at which I can go, which is physically limited. And that's exactly what we want to explore. So essentially the goal, in other words, of the next couple of hours is just to answer your question. Okay. So I'm sorry you also paid miserably to ask us. Very good. Okay. So okay, we were just saying that, okay, these guys are moving, and we can move them with different polarizations. Again, here the details are maybe for too much physicists. Okay, here are some different atomic levels, which I can couple with different colors of lasers or polarizations, and I can change the laser parameters in order to have this movement. Okay, so this is what is happening, which we saw in the movie before, and in the end, now we get each atom in parallel, which get this phase, and all of them in parallel, which means just with one operation, I can do many quantum gates, and I can operate this system in parallel. So then the question is, okay, so those are some nice ideas, but we need to make it work in practice. So it means that we will have specific problems, physical problems, and those are the problems which influence the answer to your question. Like if I am moving the atoms around, I am transporting them. How efficiently can I do that? How quickly can I do that? Okay, because I cannot just throw atoms around. I have to carry them somehow with this potential. So it depends how deep this potential is, and so on and so forth. As I said before, we needed to address them, these qubits, one by one in an array. And also, we want the qubits to react very strongly to our control and to be, as much as possible, decoupled from the environment, so that the decoherence is very long time. And then, quantum optimal control theory, so that's the point, is helping giving answer to that, because those are methods which were developed for classical control. And then, this is something which was developed also and applied to quantum chemistry. And the point is, I needed to do a physical process, which is not the typical thing that would happen. Typically, a quantum computer does not work. Okay, so we need to do something very, very special, some very specific tuning and changing of our control parameters so that we get to the goal. And then also typically in a real experiment, you have noise, so you have to see that this is working also in a real situation. So that's the purpose that we have for our rest of the lecture here. So we focus now. So I hope I give yes. Oh, there is. Was that a question or not? It was just okay. Research. It was position. So I hope that I have given you a motivation. Why we need to do this optimal control is precisely to do things as quickly, as precisely as possible, to build those building blocks, to make those n-qubit transformations in the best possible way. So now we have to focus on what it takes. And let's imagine classically what it means. For instance, classically, I could have some physical systems, okay, which I want to put, let's say, in an ordered structure. Okay, so I need also a structure where I can put these systems, okay, like a carton for my eggs. And then the proper control and outcome is I put them and I get a nice ordered state. This would be similar to my atoms in my optical lattice. But then if I do it with quantum means, okay, I actually have some very clumsy tools, because those eggs are no longer, the same size as my hands, but they are very tiny atoms which I manipulate with macroscopic tools. So it's even much worse than this, as a matter of fact. And then it means that the outcome that I could get could be something which is very, very, very bad. Okay, that's what I want to avoid. This is a very decoherent state. I don't want to break down all my atoms. I want to make sure that it properly works. So how do I get there? Well, here is an example. So this is a picture which was done in 1941. Okay, and so it means pre-Photoshop. So it's an actual picture of an actual physical process which is taking place. So there is someone who is skating. So here is like an ice surface. They are skating with some glasses. And this is not a typical physical process. Okay, if I tried to do that, I would fail miserably, and my glasses would be as broken as the eggs in the previous time. Okay, so if I want to transport something, first time I try, it doesn't work. Okay, let's assume that, for instance, let's imagine that my colleague is the chair of this session. Let's imagine that Professor Henry Martin is sitting there. He told me that I can speak for 2 hours. Okay. But actually, there are many interesting things to tell you. So I want to speak for 14 hours. So I must make sure that Professor Martin will not be able to wake up at the end of the 2 hours. So how do I achieve that? Well, I have behind here, you cannot see it, but behind here, I have a source of a very desirable liquid. A fluid which, if Professor Martin will drink it, sufficient quantity, okay, he will not realize when 2 hours are, I can go on until tomorrow. So I prepare, behind here, a tray filled with those champagne glasses, okay? And I want to deliver them to Professor Martin and fill them to the brim, and I have to transport. This is similar to our atoms, because transporting is like a wave function, which I transport in a little bowl with my potential. So I have my little balls, my glasses, and then I have my champagne, and I want to deliver it to Professor Martin over there. So how do I do that? I don't want to spill it. I want to be sure that he gets completely drunk. Okay. So, if I don't get with sufficient champagne, I will fail my goal. So I can do an adiabatic process, which is like this. No? I am not exciting the motion. I go very, very slowly, okay? And very, very slowly, without exciting the motion, without spilling my champagne, at some point, I will arrive to Professor Martin. However, there is decoherence, because this will take a long time. Okay, it's not an efficient operation, to answer the question before. So this means that since we are in Africa, champagne gets very warm very quickly. So when I deliver it to him, he will not like it. So he doesn't drink it, so he doesn't get drunk. So I have not achieved my goal. I have to do the same process, deliver as much champagne as possible, but more quickly. So I have to try again. And then since I'm a physicist, I know there is a certain time dependence between here and there. So I started with a linear function of the position as a function of time. And with this linear function, I know, so is something not working? No, okay. Should I do something in a different way? Should I not deliver the champagne to Professor Martin? Okay, okay, so I'm a physicist, so I say, okay, let's do it in a shorter time. So I change my time dependence, I will start here and I say, okay, I have a smaller time to get there. Let me go with the time dependence. So I start like this, okay, but as I am, midway, also my fidelity will have dropped, my error will have risen, my fidelity has dropped in the sense that half of the glasses are on the floor, and I do not manage to deliver the proper champagne to Professor Martin. So still, it doesn't work. And this is something that we know that whenever we have a non-typical physical process, the first time it doesn't work. But I can retry and I can learn. I have to develop a feeling for how my champagne is reacting to the motion. How do I do that? If you observe, of course, I'm a quantum physics professor, so I'm an infinitely wise person. Okay, I'm also very old, so that adds to my wisdom. So it means that I can learn. I'm a learning system. Okay. I can learn how to do that. I will observe a real waiter. What does a real waiter do? They will do something like this. So here's the tray. They incline it. They go there. And they de-incline it. And they do this not in a simple linear motion. They combine the motion of the inclination and the speed of the process in such a way that in the end, we get to the proper state. But actually, during the process, I have excited the state. Okay? It's not in the ground state. It's not the lowest energy. There is a lot of energy I'm giving to the system, but I combine it in a proper way such that in the end, I get to that point. I have to do it properly, because if I incline the tray like this, I incline, then I start moving, and then I decline, okay, that will not work. Okay, so I have to combine properly the time dependence of my process in order to get to the proper solution. And once I know how to do that, well, I have to develop a sense for what is the dynamics of the system. Doing this with champagne is different than doing it with mercury, okay? Because the excitation I have to give is different. So, but at some point, I can do something which is quicker, to answer your question. And then the point is, again, this is not really a typical physical process, okay? I probably, despite of my infinite wisdom, and now it is too late in my life to ever learn to do this. I will never be able to do that. You probably would, but it requires some training. On the other hand, it's a non-typical but possible physical process. That's the point. When you want to build a quantum computer, you want to do something which is very far from typical, but we believe it is possible. And companies such as Continuum and others, and many labs around the world have shown that it is actually possible. And now we want to do this and go beyond and do some remarkable things. Of course, we have to use all of our control parameters, okay? So if I would not tilt the tray, it would not work. So I have to use all that I can in order to achieve my goal, and then we make more interesting games. And that's exactly what we're going to show in the following. So now I have to ask myself, because, it's only 40 minutes. So how do we do? Do we want to have a break after 45 minutes? Do you want to have a break after an hour? Do you want to have no break and be destroyed? Professor Martin said that I should stop and give a break the first moment I see someone collapsing onto the floor. In that case, I should actually stop. But you have the choice if you want to break also, because of how does it work normally with lectures. Normally in Germany, people after 45 minutes are completely destroyed. They say, please stop. They beg me to go to the bathroom. Shall we do that, or how do you want to organize it?
Let's go.
Say it again?
Continue.
Continue, I continue. You are fat and strong.
Yeah.
Okay. Okay. If someone collapses on the floor, please do it with a loud thud so that I can perceive. Or if you see a colleague on the floor, raise your hand and tell me, you know, they have collapsed. Okay, very good. We just go on. Okay, let's try to go on. Now, oh, yes. No one on the floor, no. Very good.
I'm wondering.
Or maybe let's try, let me give you this, so that everybody will hear the question. Oh, yes, yes. So that's it. So he asked, if I want to realize a non-typical process, why would I use some standard classes? Why do I not use a special container? Okay. And that's of course what we do, because we start with something which is, you know, those atoms or ions or other systems, and we get the most special lasers which are suited to contain them. We will use lasers which will couple strongly to them, which will exert a strong force on my atoms, so that the container is as tight as possible, so that there is no spillover effect as much as possible. But this also has limits, in the sense that I cannot, an atom is not something which I will be able to sort of pinpoint like a classical system, obviously. So there will always be a little bit of sloshing in the wave function. So once I have done my job in terms of getting the most specialized container for that, still I will have some imperfections, and that's what I have to take care of. So that's very important. This will not work if I start with something which is just anything, take an atom and do whatever. It will not work. I have to do a lot of homework before to get the best possible technology, but even that is not sufficient to achieve the enormous level of precision that I need to, in the end, have these many millions of qubits. Okay, so that's the reason why we still need this technology. And that's, of course, a very important question. And also, it relates to the next slide, in the sense that the question is, okay, now I know what I want to do, but is it controllable? So I have a certain system, okay, with certain physical ingredients. Will it work? I don't know. So let's take one famous example of control, you know? So let's say that I came very late for my lecture. The lecture was at 9. I drove, and outside on the street, there is just a parking space for my car, but the parking space is epsilon longer than the car, with epsilon an arbitrarily small quantity. And of course, there's a parking theorem which says that I can park transversely a car in a space epsilon longer than the car. How do I do that? Well, how do you park a car? Well, typically, you are sitting in the car and you're a computer scientist or a physicist, so you say, okay, now I have to park. Where is my dynamical algebra? Right? That's what you do every day. And my dynamical algebra means what is the dynamics? Algebra means, you know, composing operations. So what are the operations which are available for me? And they are, you know, going back and forth and then turning the wheel. Certainly, I do not have this operation directly in my car, but my dynamical algebra means what happens if I compose these operations and I do many of them. And of course, if I do many of them a lot of times, then at some point I will be able to park. Even a machine can do that. Okay, you can now buy machines which do that automatically. But the point is, again, you know, how long does it take? So that's the question which we were asking before. And how long? It depends, of course, on how well the car can steer, how longer is the space, so physical parameters. But there will be a limit, a physical limit of the number of operations that I need to have. Probably it will scale as inverse epsilon, okay, obviously. So that's a simple classical example. In a quantum situation, as we said before, we have to go from an initial state to a final goal state which we desire. In the champagne example was, you know, the state with all the champagne, very chilled, in the proper place. So essentially, there is a goal we want to achieve. And what is the difference if we have a quantum system? It's quantized, so it means that I only have some discrete states. And some of these states, like electronic states in an atom, they will be coupled to each other. So typically we have some matrix elements, some couplings, which enable some transitions between some of these states. But in this situation that we have here, schematically, I still do not have a path to go from the initial to the goal state. So as I said before, I have to excite, I have to give a kick to my system, I have to shake it in some way so that I create additional couplings, okay, dynamically by shaking it. And that means that now I will have different paths. I could have a blue path to go there. I could also have a green path. And again, the question is which path is optimal in the sense of both being quick and also being as effective with low error as possible. That's what we need to search. So what I said before, if I want to create some coupling, I need to shake my system. I need to kick it. So those are wiggles. Okay, I have to wiggle my system in some way. Let me give you examples, classically, why such a wiggle intuitively can help us. So here is an example of a race between two balls. Okay, so we release two balls A and B with the same speed and same mass, on one end of these waveguides. And then we ask the question, which ball is coming to the end, which arriving first? Okay, it may seem obvious. There are three possibilities. First one is ball A wins. Second one is ball B wins, or third, it's a draw. One could think, well, it's the shortest. Another one could think, well, but energy is conserved. So, the speed will be the same. So the time at which they get there is the same. So let's take so now we are documenting. So it will be forever live streamed on YouTube. Okay, what is your answer to this question? We have arranged this moment with very high precision, okay, that we cannot escape, either eternal fame or eternal shame. No, it's really up to you. So now I will ask, and we are in web world streaming. Who thinks that solution 1 is the correct one, so that ball A will get there first? Who thinks that solution 1 is the correct one? So your hands up, please, because there are screens. So there are a few people. Okay, which think that the first. Okay, very good. Now, is there anybody who thinks that solution 2 is the correct one? You think that. 2 people think that. 3 people. That. Okay, so it's about like before. Who thinks that this is a draw? Okay, so you're not allowed not to think. Important thing to check on what to mention. So you must have a think. Okay, but yes, please.
Are they all under the same force or different changes in force for the force?
No, sorry, I should have specified. I took for granted that this is like some vertical. So we are in a gravity field. So these are really some physical paths which some particles are taking. So there's the same gravity force for both of them. And of course, the friction is the same, so they are rolling, and so everything, all the conditions are the same, and also the initial velocity is the same. So they have completely. So some people got it right. Maybe they have already seen the solution, right? And but one may say the fact that so the purpose, of course, was not to eternal shame for any of you, but only eternal fame for the lucky ones. But the purpose here was to show that it's not obvious. Okay, the first time that I was presented with this, I didn't guess it right. Okay, because one could say, oh, energy is conserved, so it will be a draw, or geodesic, it's shorter. But actually, why is it like this? Well, I have for anything. I mean, of course, we just have YouTube here with us, and you know that for any question in human knowledge, there is an answer on YouTube. Okay, so you just have to go there, and so you get the answer. Here you go. You release the 2 balls, and then that's what happens. And then you do it maybe more slowly, and you see that this ball is accelerated then it is decelerated. So of course, at the end, the speed is the same, but during the process, like before, there is some excitation during the process, and there is the de-excitation. But during the process, in this segment, the second ball beam is faster, so it gets there first. So, and after you see it, you say, oh, sure, obvious. But my point was really to show that there is something non-trivial, something which we would not intuitively immediately guess about how you can play with the parameter space. And if you play some tricks with parameter space, this is one single wiggle, okay, just one excitation and de-excitation, then you can indeed get closer to the goal and in a faster way. That was the purpose that I had here. So there are other ways. So this one is a single wiggle, but if I shake things, here is another classical example, is the Kapitsa pendulum, in which if I shake something, I have an inverted pendulum, okay? So it's like I mean, it's the same way, if you wish, when you have a stick, which you're balancing on your hand, okay? But the thing is that if you're balancing a stick, you are doing some feedback control. Like you're watching the thing, you are sensing and looking that it is about to fall off, and then you correct the position in such a way that you follow it, okay? But the interesting point is that this works even if you do not have this feedback. If you just are shaking it with some given frequency. So this is the inverted Kapitsa pendulum, in which I take the same thing and I shake it with some wiggles which are regular, sinusoidal, and then what happens is that there is as a function, so for different amplitudes, of course, of this shaking, as a function of the angle, there is a minimum around the vertical, in the sense that if I shake it, even without checking where the thing is, then I can keep it straight. I can keep it from falling. And this is just by giving this shake to my system, so that if I do not drive it, it will fall down. If I drive it, it will stand up. So wiggling things, oscillating things, shaking things is something which can be very useful, and we will see how this is useful to stabilize, even against perturbations, because it can have some noise. This is maybe not precisely the initial position, precisely vertical. It could be a little bit different, but it gets stabilized. So this is a simple way of stabilization via control without feedback. Okay, so we are going to do other examples of that with our quantum systems. Now, we want to use these ideas with quantum systems. So this is the situation that we had before. So I showed this, potential transporting back and forth, the red and blue potential, going with the atoms. In this case, it is not red and blue, it is dashed and solid for 0 and 1 states. And there is an initial state, and there is an evolved state. And I want that after I manipulate, so my control parameter here is, my initial state is of course that it is in the each atom in its well. My control parameter is the distance between the two parts of the potential, and then my evolved state is when they come together. And I want to maximize a fidelity, to minimize an error. So this is, for the non-physicists among you, this is a measure of the projection. So how much the goal state coincides with the state that I get after my process. Essentially, here I am counting with this how much champagne was on the floor. Okay, I compare what I wanted to have with what I got, and then this gives me some errors. So I want to improve on that. And this is where we use special wiggles. I said before, it's about tuning properly the whole process to get there. So let's see how it works. And there is, here I have to mention one important thing. There is one theorem in theoretical or experimental physics, which is always valid. This theorem says, given any problem in theoretical or experimental physics, there exists a Russian who solved it 40 years ago. And pupil, relative, or friend of said Russian will stand up, usually from the bottom of the seminar room, after the talk, and say, we do this in the military school. And so this is a fact, okay? It is a theorem, and it is proven by experience. And so the only thing that changes from problem to problem is the name of the Russian, and in this case, the name was Krylov. And the existence of Professor Krylov was proven by the fact that when I gave this first part of my talk a few years ago on Russian television in front of 15 million viewers, okay, which is 50% more than Festival di Sanremo, okay, in Italy, Professor Krotov called me an intent for algorithms. So he does actually exist. Okay? So that the theorem is, and it says that if I start with some initial state here, and I want to evolve, so here is my unitary transformation, the same operator U, which I want to realize for my quantum gates. It depends on the total time, hence the question about speed. It depends on the distance, the control parameter, and then I get an evolved state. And then what do I do? So this algorithm works like I have arrived here, and I see that my champagne is on the floor. So I want to improve. So I go back in time, okay, and I start wondering, well, what would have happened if I moved my tray in a slightly different way, okay? And I start calculating what would have been the evolution of that, so that I say, okay, maybe I should have done something different. If I did, a tilt in a different way, I would spill less champagne. So I recalculate, going back, what I should have been doing in order to get a better result. And then I go, and then maybe it doesn't yet work well, so I go back and forth many times until I get low error. So, and the way in which I go back and forth is that I update, I take my pulse shape, my time-dependent parameter, and I change it with some functional, okay? I have some algorithm which tells me, okay, here is the state which evolved, here is the state coming back. And how do I now change this parameter in order to improve? The algorithm by Krotov is just that you use some gradient. It's like a Lagrange multiplier, okay? For minimization, this is something which is completely familiar to both physicists and computer scientists. It's actually, optimizing on a gradient is the basis actually of artificial intelligence, of machine learning, if you wish, okay? So it's something which is pretty standard. You look for the gradient, you're asking yourself the question, okay, in which direction should I change in this infinitely dimensional space my function in such a way that I get a better result? And then you iterate, you go in cycles, and at some point you will get a better result. So let's see how this works in a specific example. This example is the one with the atoms moving around, okay? So I have, in this case, I calculate this in relative coordinates, so in a reference system which is about the distance between the two atoms. So I start, I had the two atoms before in two different wells, and I start with in relative coordinate. It means that they are far away from each other, first order distance. Here is the quantum wave function. I want to bring them close to each other, where they are on 0. And then when I have done my homework, so my homework in terms of getting the best possible container consists in making the laser so strong that this thing is as localized as possible, okay? So that I can transport it. But I cannot make it too strong because a too strong laser will just burn a hole through my experimental apparatus. So there are physical limits for that. So I have to deal with a certain frequency, a certain traffic frequency, and then I want to move from here to here. And here I have my control parameters. So first of all, the distance from 3, you see, to 0, moving to the origin. But then, you remember what I said before with the waiter. You have to use all your control parameters. So you have to not forget to tilt the tray. So this time, what can I do? I can massage a little bit. I can juggle a little bit. I can, squeeze a little bit this function by changing the strength of this, and maybe this will help. And I will do this according to this Krotov algorithm, going back and forth. So first, I try to go here, and I will see how much fidelity I have. It will not be 100%, you will see 85%. And then I go back and forth until my fidelity reaches close to 100%. So this is the first time, you see it is not really symmetric, and fidelity is 85%. Then I go back again, and it already improves to 97%. And you see here that I have this kick and counter kick. I am exciting my atom. You see, I am massaging it in such a way that then it goes to something which is very close to 100% fidelity, low error. And I have this kick not only in the position of the potential, but also in the strength of the potential, and also a counter kick. So I am exciting the system while it is moving, and then I am de-exciting it exactly as I did before with my champagne. So that's how it works, and we can develop an intuitive picture of this. Why does it work? Well, it's a quantum system. So it has different energy states, and these energy states will change with time. So what I want to do, what is the analog of the adiabatic, the very slow process? I start, so let's say that I am in one phase, this would be a many-body state, so for material science, okay? A certain material in a certain phase, and then many-body quantum state, and then I want to go to prepare another phase. How can I do it adiabatically, slowly? It means I start around here, and I go slowly, moving from one end to the other, in the sense that, I stay almost on the ground state, and I get to the other side. Now, what happens if I want to do the same process quickly, but without optimization? Then I squeeze the time as before, so I now go fast. And there is a problem. There is another Russian here, his name is Landau, okay? So this is a so-called Landau-Zener crossing. It means that there is a probability of exciting my system and going into some high energy state, which is inversely proportional to the speed. Sorry, it's proportional to the speed and inversely proportional to the gap. So if I have a small gap here around this small energy gap, if I go too fast, I will have some energy, and then I do not get to the phase that I wanted to my low energy state. So if I do optimal control, what it does, as we said before, I am exciting more in the beginning, and then it converges to the desired state. Because those are quantum states, there are superpositions. So there is interference between these states. I can have constructive interference such that the probability of getting the final state is exactly what I wanted, and destructive interference for the states which I do not want, so that I really converge to what my goal is. So that's the idea why the whole thing works. And now we can start looking a little bit at some examples of that. Now we have, so yes. Oh, I cannot hear, so.
We have a short break.
Short break, okay, excellent. So someone asked for a short break. I think there are no corpses yet on the floor, which is always very advantageous situation. We are preventing people from collapsing to the floor. So thank you very much for this wonderful idea. We are going to have how much? A 15-minute break? 10 minutes break is the proposition. Okay, 10 minutes break. So we reconvene at 10:13. And I also need, since I'm an old person, I also need to know where I could powder my nose. And I hope that someone will help me. So anybody knows where I can powder my nose?
Hello, hello. It's connected. Hello, 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 hello. Hello, 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 hello. hello, 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 hello. I hear you. Hello.
Let's get ready to start. Maybe we wait for a couple of minutes. Some other things. George. Okay, so I told that we can start. But it's, I see that some colleagues have not survived the first hour and they are not showing up. Let's hope that nothing too terrible has happened. But what we're going to do is to answer the question of your colleague, which is now absent, which is how can we push the speed of how can we push our control to the limit in the sense of using it to do things as quickly as possible. The question is, my process, how fast can it be? And then, of course, I try to do it once, and then I try to do it twice, and then. So until, of course, things break down, and I can no longer get a proper fidelity, a proper low error for my process. And this is, of course, we know that always that energy is related to time, and vice versa in quantum mechanics. So there is broadly speaking, even though it is not formally correct, as you may know, a time energy uncertainty principle. It means, in essence, that the time that I have, the minimum time for my process, will be dictated by inverse energy scale, either of the energy level which my system has, or the variance, the difference, some relevant difference in energy that I can have there. Yeah. So this is something which has been proven more than 20 years ago formally, and we are going to investigate how to make it in the sense that we know that formally this is the fastest possible. You cannot go faster than that, but it doesn't mean that you know how to go that fast. And it is actually optimal control which will tell us how we can go that fast. So here is a simple example in which, it's this Landau-Zener crossing I mentioned before, okay? So it's two states which are getting closer and then they depart again. Here is the Hamiltonian for the physicists among you. I am not going into details of that. What I am saying is that here is a view graph of how I can get error decreasing and getting smaller and smaller and smaller as I increase the number of iterations of going back and forth with my algorithms. So if I do more and more tries, of course I expect that this error will go down. However, I notice one thing. that if the time I try this transport problem that I showed before between the two sides of the standard and the crossing with shorter and shorter times. And here I have curves of how the error depends on the number of iterations for different total times. So I can see that if the time is long enough, like here, you know, with in some units of the harmonic oscillator is 1.6, then my error point keeps going down. And you know, if I lower the time a little bit, then the error still goes down, but slower. If instead I have a time which is too short, the error will saturate, will never be able to reach a sufficiently low level. And you know, these curves, the curvature is telling me, is it now converging or not? So I can plot the curvature and see that there is a certain value of the time, which is about this 1.58, at which it saturates, and I cannot go faster than that. So this is a way in which, for that specific time, optimal control will give me the operation which goes at the speed limit, so the maximum possible speed, and will enable me to construct that to make sure that the whole process is working. Actually, if I look by lowering the time, so I have this sort of speed limit time, and then I can normalize all the time as a function of that, and I see what happens to the final fidelity that I get at lower times. So this is the fidelity, and this is the time times the energy difference, and we see that there is a cosine. Actually, it's a cosine because this is the inverse of plot, but anyway, there is a cosine dependence, so there is a universal dependence. In other words, if I do my process faster and faster for shorter and shorter times, oh, oops, I missed the, okay, never mind. So if I do my process for shorter and shorter times, up to a certain point, I will be able to do it perfectly. And this point is the quantum speed limit. But if I try to go quicker, below this time, then it is impossible to get zero error, and my error will start growing like a cosine square, which corresponds for the physics system of view to the fact that I have a vector in Hilbert space, I am rotating it, and then I go with maximum speed, but at some point, if I have not enough time, I will end up close, but not exactly at the state that I wanted, and the overlap between my state that I achieved and the state that I wanted is a cosine square. So this is an explanation for the physics system on view, but in general, it means that I can do processes faster and faster, but only down to a certain time. And now we want to see how this works in practice. And we want to use it in a certain configuration. For instance, I can have, here is an ion trap quantum computer, again, something which Continuum is very strongly working on. And what we want typically in such a processor is that we start with a certain state in a certain position, and we want to move it to another region of our processor. Again, this is a transport problem. In this case, not transporting atoms, but transporting a state. So I have an excitation. In this case, I have a certain chain of spins, and all of the spins are in state 0, but initially the first one is in this superposition, alpha 0 plus beta 1, a generic quantum state. And this is what this my qubit, which I want to transport to the other side. So my final state that I want to achieve is alpha 0 plus beta 1 on the other end of the chain. How can I do that? Well, there is, again, like in the beginning, in the adiabatic example, I can use the Hamiltonian. So this is a spin-spin Hamiltonian. It's interactions between the spins. And I can have a magnetic field which is inhomogeneous. It has a minimum in the beginning on the left hand where I have the qubit that I want to transport. What can I do? I can do adiabatically moving from one side to the other, which is such that close to the minimum, the spins can flip. So it's like transporting this excitation to the other side. And it does work adiabatically using my control parameters, which are the strength of the field and also the distance from the beginning. So now we are going to see a movie, how this is actually working in real life, in the sense that I have my different spin sites and all the population, so my excitation that I want to transport, my signal, my qubit, in the beginning is sitting on the left end. And if I go slowly, I will be able to swap from one side to the other, and going from here to there, and I get with a very good probability, very slowly to the other end, and I transport my qubit. Now, if I do it faster, but not with optimal control, what happens is that, I leave, so here are my glasses on the floor. Some population of my qubit, of my spin, due to this famous Landau-Zener crossing that I said before, because now I'm doing it too fast with respect to the strength of my potential, are such that I leave some population behind, so I only get to less than 50% to the goal that I wanted. So here is where optimal control comes in. I use my Krotov algorithm that I mentioned before, and I run the optimization. So here are the time dependence of the strength of the field and of the position. And then what I do is, as I iterate, I change the shape of this. I change the time dependence, so I get this kick and this counter kick, which as the iterations move forward, they develop. So in the beginning, I excite my system, and then I de-excite. And in the end, I get this counter kick, which will bring all the population in the desired state. Let me show the movie how it works. It's like juggling my spins, okay? So I start from one end, and then I start moving, juggling around, so I delocalize them, but then I catch them back. This is what the optimization is doing, and I can study how this depends on the time for different times. I can get there 200 times faster than the adiabatic process, which is very important if I have the coherence waiting to destroy my quantum computation, and I can still do it with very high fidelity, very low error. So here is a plot, a color plot of, as a function of the size, the number of spins that I have, how long is the time in which I can do this process. So if I compute the fidelity or equivalent to the error for such a process for different times, I will see that if the time is bigger, so the time now is normalized divided by the number of particles, so I get a flat border here, in which I go from very high fidelity, low error, okay, 10 to the minus 4 error, and here, for low time, I get to an error which is order 100%. So there is really a hard wall here, and this is really this quantum speed limit I wasn't discussing before. So this is the way in which we can actually answer constructively the question that was asked before, how quickly can we do things? And then, obviously, if this is about swapping from one side to the other, it will take any such swaps. And in an elementary way, you can say, of course, it has to go linearly with n, and optimal control allows you to make it, to construct the process which does that. In fact, even to do a little bit better, because if you have a swap from one side to the other, you will have a dependence like this of the time on the number of spins that you have. And instead, with optimal control, you can beat it by a certain factor. So you know that you cannot do better than that. Very good. So now we want not only to push the limit in terms of very fast process, but also we want to push the limit in terms of very big. So how big can we make a quantum system that we try with this method? So I want a very big ground state that I prepare for a bigger system. And so let's look how it works. Again, here is an example of something in which I can use. It's no longer, before I showed a cartoon of these levels, okay? Here is an actual quantum model with many spins together. And the way it works is that I go with different speeds from one side to the other. And here is where there is a small energy gap. So I get this Landau-Zener crossing. And again, yellow is I go adiabatically very slowly, I remain in the ground state. Red is I go linearly without optimal control, and then it goes up. And here you see in optimal control, if I optimize this particular model, I get some excitations, and then I go down to the ground state. And again, I can do this at the speed limit. Because I can see that not only for this particular model, but even if I try to do an adiabatic version of a Grover search quantum algorithm for a quantum computer, and even if I do this Landau-Zener simple crossing that I showed before, in all cases, okay, the error as a function of time, if I renormalize by the speed limit time t star, is universal. So there's really a scaling such that all of these systems practically have the same behavior. And it means that I know what is the minimum time by which I will be able to get a low error transformation. This is with optimal control, in other words, I have zero infidelity, zero error for all times above the quantum speed limit, which is again of the order of the inverse energy scale in my system, and cosine squared below. And instead, if I didn't use optimal control, I went with a simple linear process, I would have the error going to zero only for very long times. So all this area here is something which I could not use for quantum computing if I wasn't using optimal control, but I can if I do optimal control. So that's an in-depth analysis of this question about how quickly can we go. And now, the method I showed you, because now we are asking the question, not only how fast can we go, but also how big can we go. Because, as we said in the beginning, a quantum computer is a system with many qubits. And I want to manipulate all of them also in a very fast way. So the method I showed to you, so this is a violation of the Racine theorem, okay? Because that works only for small systems. But if you want to do optimal control of a big system, you have to develop a new idea, which is what we did, is the Choc random basis algorithm. And why is it called like that? Because, again, for my optimization, I start with a certain time dependence, which is this C control parameter as a function of time. And then I want to update it. Here comes my CRAB, Choc random basis, and I want to update it. But instead of looking in the whole space of infinitely dimensionally many functions, I am just going to a simple sum of a few basis functions, could be sinusoidal functions, could be different things. And then, but the important point is I only take a few of these components, typically 4, 5, 10, and then I update my pulse. And what does this imply? So what this does is essentially to have a few parameters by which I describe my problem. So it means that my fidelity or my error, my figure of merit, will depend on just a few parameters. Let's imagine that I have two such parameters, so I have only two components. And let's imagine that my initial goal is not good. So I want to get low error, so I want to be here. But in the beginning, my initial guess, like in the example I gave before, has a high error. So I want to optimize in a simple way. And this can be done with a simplex method. So, in this landscape, since now it's a simple landscape, I can go down by having this little polytope running down, this little triangle running down, and it gives me a certain pulse shape, which is updated without having a gradient, so it is much easier to compute, without having an analytical solution, and I can do it for any figure of merit. So I can also use it, since I do not need to calculate something, I can also use it in a closed loop. Okay. This is what we call the plug and pray approach, because the plug and pray normally is, you plug your algorithm and you pray, and hopefully it will work. But if you put it in a loop, it will instead keep checking and improving based on the real data. So that's an example, again, of reinforcement learning. That's an example of how we use machine learning for, essentially, in machine learning, you also have big landscapes like this, and you have to find the best way to minimize. The famous problem in artificial intelligence of barren plateaus and these kind of things, which our friends from computer science know very well, is due to the shape of this landscape. Here is the same. Only the landscape is not related to learning some large language model. It is just related to making a quantum computer work. So we can do that, as I said, both in open loop and in closed loop. So what we do is, for instance, here is an example with diamond in n centers. So those are atoms, if you wish, so that nitrogen atoms which are trapped in a diamond, in the sense that there is a vacancy, which is Nv means nitrogen vacancy center, there is a vacancy, so a carbon atom in the diamond which is missing, and then it is replaced by a nitrogen atom, and here is the Hamiltonian, and there are several parameters for controlling that. And of course, what we do is we update the control, the external radio frequency field in order for us to get a proper quantum operation. And of course, we do it with some sinusoidal functions according to these methods that I just described. So we can take into account that not only I have my quantum system, but also once I give a certain part shape, there's an arbitrary waveform generator which is supposed to give it and then amplify to the system. But this all electronics is changing the shape of my files. So I can take that into account in optimizing the whole thing. And here's what I get, that if I want to do a bypass, so a rotation from 0 to 1, then instead of going directly, I take a detour in the Bloch sphere. You will be explained, if you're not familiar with that this is a representation of a qubit. So I take a detour, instead of going from state 0 to state 1 directly, I go around and I get this with a much higher fidelity. And same if I want to do from a state 0 to superposition 0 plus 1. We have validated experimentally, of course, that this works. So this is the measurements, the tomography, which shows the fidelity of this. And the next thing is that it can also be done in a closed loop, because what I showed is we calculated that. And here we can also do that. We have a certain laser addressing the diamond sample, then read out the signal, and we improve, we get a certain fidelity. And with our algorithm, we change the control in order to improve the fidelity. So it means that instead of having the student, which is locked in the lab all night and turning knobs, okay, the student goes to bed, comes tomorrow morning, and the thing is working by itself, okay, in this way. So at midnight, okay, time equals 0, the fidelity was equal to 50% error for a given Hadamard transform. So in this case, it was a quantum gate of a pi half rotation. The technical detail is not important. The important point is that in the beginning, when I try it with a simple part shape, like this square part shape, I only get limited fidelity, and then I update, and in the end, I synthesize a pulse which is different, quite very different, but in the end, I get to a fidelity which is 99% without human intervention. Okay, so this is automatic learning, and in fact, this is something which can only work over the internet. Maybe we will have time to address that in a moment. But before, I want to show you how this works, because this epicenter is still 1 qubit, how it works, as I promised before, how can we make it bigger and bigger? So if we go to a bigger system, well, maybe I can skip this because this is not so relevant for quantum computing. Yes, no, sorry, the next one. Yes, so this is when we apply it to a many-body system. In the sense that we have, you remember in the beginning we said we have those eggs and we want to put them in the egg cardboard. So it's this optical lattice potential, and we want to have in this optical lattice potential 1 atom per site in order that we can use this as a quantum register. How do we produce that? We can start from a superfluid, so a Bose-Einstein condensate, a cloud of ultra-cold atoms, and then we start by switching on slowly the laser field. Again, adiabatically, slowly I switch on this laser field, so this potential becomes higher and higher until I get a transition. It's really a quantum phase transition between 2 different phases, as we said before, to a state in which I have an insulating state in which I have 1 atom per lattice site. What I want is to use this for a quantum register, so I need 1 atom per site. So if I get 2 atoms here and 0 atoms there, that's bad. It will not make my quantum computer work. And this is exactly a kind of error which can happen if I do it quickly on a much shorter time scale. So before we did this work, people knew how to realize this with the proper control parameters. So the control parameters are J and U, especially J, so the strength of the coupling, which depends on the height of the potential. They could do it adiabatically, slowly, but they did not know how to do it quicker. So that's where we came in. This yellow, again, is the pulse shape which was adiabatic in the sense of going over 150 milliseconds. And here is, we wanted to do it 10 times faster. And we could either do it linearly with the red line or using our optimization, which is what was synthesized by our CRAB method. And here is the result. So what you want, this was an experiment which was done by Emanuel Bloch, Munich, where they had one of these quantum simulators. And here they occupied the number of atoms in the central area, the central region of my quantum simulator. I want one atom per lattice size, so I want the density 1 and no difference. So what I do if I do not optimize is instead I get 15% density, 15% probability of having errors in here. If I optimize with my pulse shape, then I get essential unit probability. So in this way, I can not only juggle one individual atom, but I juggle many of them together to getting into this situation in which there are one in each point of my end cardboard. And also here, I see the quantum speed limit. This cosine squared that I said before, if I reduce the time, then my error goes up to, of course, 100% if I want to do it with a very, very small time. And the important point is, in the experiment, here is what we would achieve at this speed limit if we didn't optimize. So fidelity 50%, and instead we can bring it down to the noise floor, essentially, of our system using optimal control. So we can say not only how quickly I can do the process, but we can also say in which way we can realize this technological process. And as I said before, it also works online. Like I have an experiment in some place, could be even, in a different continent. Actually, we have done, I will show results afterwards of an experiment done online with the United States. And then, so locally here in your lab, you have this RedCrab client. So our the program, which communicates with our server, which is in our lab in Munich. And then this client is measuring what happens in the experiment. And then the update of the pulse happens via our machine learning methods, and then gets fed into the system remotely to improve the experiment without the need for, indeed, human intervention in this sense. We have even put it in an optimal control suite, so you can download this from GitHub. This is specialized for this experiments with NV centers, but these methods also work for atoms. And so there are different algorithms which are integrated there, and you can really use it to, download it and use it for optimizing your experiments. And now a few examples, because we have still a few minutes, I think 20 minutes, a few examples how we can, now we have said one example of how we can put one atom per lattice size to make a quantum register, the basis for a quantum computer or simulator. Now we can also show how we can use these methods to prepare the initial Bose-Einstein condensate, the initial state with very cold atoms. This is something that we did now 8 years ago in the context of quantum gaming. Okay, so there was this group in Denmark, the group of Jakob Scherson. They were interested in actual people, not like us, physicists or specialists, but really regular people play with quantum systems to see, first to make them understand that, and also to see what is the behavior of sort of natural intelligence in this context. So there is a website, and at some point you could connect to that website, and it would be presented with this video here, in which was telling the story that you have a cup of some very hot fluid, which you then pour in a different cup made out of lasers, and then you just do it in a very messy way, okay? And so this is still quite hot, and then you tune the laser power by lowering it. This is evaporative cooling, with which DCs are formed in such a way that it becomes very cold. This is the representation of the experiment. Atoms are loaded to a trap, which then is changed in intensity, and the people online, they could play with the time dependence, how the intensity with this graphical interface, how the intensity would be changed with time, and then test. See, so the experiment would actually run. So someone would try some path shape, the experiment would run over in Denmark, and then they would get a score, which would be the number of atoms which would be in this final condensate. The more atoms, the higher the score. And literally thousands of people played this game. And it was interesting for us because there was this user interface that you see here, and we could plug in our algorithm to see whether we can also make it work. And here is the result. Well, unsurprisingly, okay, the machine outperforms human players by 20%. It's not surprising that a computer can do better than humans. What is actually surprising in this particular experiment is that humans could do this well, okay? Because they would develop an intuition. So there was even a chat on this website in which people were saying, "Oh, I tried to do that, but then the other didn't want to follow, so I tried this alternative, and then it worked." So with intuition, they were able to steer the system. For us, it was important because this was the first time in which we showed that it works really online. So, well, this is a little bit too technical, so I will be quick on this. So this is a way in which you can use essentially neural networks to study, simulate the landscape of optimization in order to understand how this could properly work, but maybe we don't go in details into that. And now I want to, so this is a picture which you get when you ask ChatGPT, please show me a picture of the fastest Schrödinger cat that has ever been created. So this is what I get from ChatGPT for that. Because going to the quantum speed limit, we wanted to get, for a certain atomic Schrödinger cat, a superposition state, we wanted to get it in the fastest possible way. So here's how it works. It's an experiment which has been done, by the way, in the group of Dieter Meschede, who is also here present at the school. And again, you see the famous potential with red and blue atoms, which move with respect to each other. You see the realization, how it is done, because the details experimentally, different polarization, different colors, and so on. And the point is that they can control the position of the lattice in a very, very precise way. So what I had shown before in terms of transport was theoretical results, but we wanted to test it experimentally. And the point was, again, we have this wave function, which we start from here, and we want to bring there, and we want to see what is the speed limit for that. So we need to have this very specific control, which they can realize. And so we wanted to check experimentally whether actually this feature of the speed limit, the fact that the error, can stay zero down to a certain time and then it diverges, whether this is actually happening. And here is actually the result. Okay, so the lower curve, the purple dots, is what you have if you do this transport problem, but without optimization, linearly. So if I do it, since it is a harmonic oscillator, if I start linearly, I will excite some motion of the wave function inside my system. And then there are some times in which if I catch it back, it will stay there. So I can get a high fidelity, okay, for given times periodically. But if the time becomes too short, then I am no longer able to get 100% fidelity, but it becomes lower and lower. Instead, if I optimize, unsurprisingly now, because now we have seen several examples, I stay with unit fidelity down to this point here, in which there is a bend in the curve, and here we get the universal cosine square behavior, and this is the quantum speed limit that we have seen experimentally. So this is really having done a transport process, as we said in the beginning, experimentally at the lowest possible time, given the particular system that we have. And then, how do we create a Schrödinger cat? Because again, we do the state-dependent transport, like I said before. So we move the atoms back and forth, and we can check at the end with an interference experiment that actually this is still a quantum state. And we can see the contrast of the interference experiment, which tells us how much my experiment is coherent. And also here you can see that, going down, down, down for a certain, down to a certain time, which is again 100 times shorter than adiabatic time, I still get unit fidelity, and then the universal cosine square behavior below that. And this is, at this point, I actually created a Schrödinger cat because in this situation, I have one atom which is at the same time in the state down here left, and in a superposition with the same atom at the same time in state up on the right. So this is the smallest Schrödinger cat that you can have, and you can realize it at the speed limit, which is given by this point in the curve via optimal function. So this is instead what I get from ChatGPT if I ask what is the fastest Schrödinger cat that has ever been created, because this is what we have been doing with the group of Misha Lukin at Harvard. So in this case, again, it's a many-body system. So again, before we had different cartoons, okay, for our many-body system, and in this case, instead, it is a real level scheme of their quantum computer. So they have this, as I said before, these Rydberg atoms. So they are excited neutral atoms. They are in optical tweezers, meaning that there are some laser fields which are, created by some acoust-optical modulator, and then you trap each atom in one of these optical tweezers. You load them. In this case, it's not one atom per side, but they are in some sites they are empty. So you compactify them, you bring them together, so that in the end you have one nice string of atoms, and they are all in the same state. And now what you can do is you change the intensity and the detuning, so the frequency of the laser fields which are addressing those. And by changing the detuning, you have, again, this is a control parameter, which makes for a phase transition from a state in which they are all in the same state to a state in which they are in superposition of 0, 0, 0, 0 in the beginning, going to 0, 1, 0, 1, 0, 1 plus 1, 0, 1, 0, 1, 0. So this is a superposition state, which again is the same of GHZ state, an entangled state, which is maximum entanglement for a given number of atoms. It's a Schrödinger cat in the sense of a superposition of all atoms in 0 plus all atoms in 1. Okay, so two distinct states of an increasing number of atoms. And we wanted to prepare this with the smallest possible error. We actually published this in Science a few years ago. And indeed, the way it works is the following: that, well, you have your tuning and your intensity of the laser, which are changing with time, calculated by our algorithm. And at the end state, you have just population in these two possible states, 0, 1, 0, 1, 0, 1, and 1, 0, 1, 0, 1, 0. And you can check that this is a superposition which is with quantum coherence, because you can do an oscillation in your system such that with this interference, the visibility of this interference is again telling you whether actually there is entanglement. So here there is fidelity 54% for 20 atoms. The way it works is that if you increase the number of atoms from top to bottom, you have these oscillations which become smaller and smaller. And so for 20 atoms here, it's just above the level of what it would be entangled. So it's just above 50% in the experiment, which tells you that with 20 atoms, we managed to get GHZ entanglement this was at the time the largest entangled state which was created with atoms. And this, as you can see here, would not be possible without optimal control because, if you just do a simulation of your system with the optimal control, of course, you will get a higher result. Then it becomes worse because there are imperfections in the experiment. But if you do not use optimal control, then with 20 atoms, you would be already below this threshold. So only using optimal control can you go this far in creating this entanglement. And here is where I'm showing you that, as a matter of fact, you need to excite the system. Because here is, so below here is the population of the, so how much amplitude, probability amplitude I have to be in an excited state. Like I said in the beginning, when I move my system, I am exciting and then de-exciting. So during the process, I will have some component in my quantum state, which is away from the ground state. So this is this population in red here. Of course, at the end, it comes down to being 0, but in between, it becomes bigger and bigger the more atoms I have, which means that if I want to achieve that process, I really must excite and then de-excite my system in a quantum coherent way across all the atoms. So that's how that works. Now, since I have 7 minutes, I could say some words about how we use these methods also to go beyond just the firmware level and higher in the stack for compilation, but maybe that would be too much. And since I have not gotten some questions in the second hour, I guess, of course, it was a lot of information, so it would be not surprising if you're a bit tired, but maybe I should stop here, and if there are questions on whatever I said before, we can take the last minutes to answer them. Yes, maybe we can. I don't know if we will now.
My question as the way depending on the number of sponges you cover, there is this one in so information and all can
for all this matter. So the end goal was to achieve, to reach a final state in my process, which would correspond to a quantum transformation, which I think was to be the quantum computer. Okay. So in the case of transport is necessary in a quantum computer for connecting different qubits, which may be distant, like qubit 12 and qubit 37. Now I want to do a quantum gate between them. So if they are atoms or ions, I have to bring them close to each other. So I have to do that, and the goal is to bring them close to each other for them to some other operations. And the goal quantitatively is to start with my atom in the ground state, and then end up with an atom elsewhere, still in the ground state, because then I can make my quantum operations which are the low level. And the goal is to do this in the shortest possible time as well, because there is incoherence, which will degrade the quality of my qubit if I take too long. So what we are comparing in those view graphs between the optimized pulse and the non-optimized pulse is what is the error, the projection of the state that I get onto my goal state. In other words, on my ground state in the final position. And the projection between the boundary vectors is telling me how much is the probability for me to achieve that goal. And comparing the optimized way and the non-optimized way, we see that optimal control, like in this last slide that I showed here, allows to reach my goal. In this case, the goal was being in a many-body state, okay? in a ground state or in this entangled state of many atoms. But the point is always that I compare what I can achieve in terms of fidelity, in terms of low error, with control, with what I can achieve without control. And in many cases that I showed, optimal control allows you to reach the goal, which is otherwise impossible to achieve. Did I answer the question? Well, this was very useful because it was a very useful recap of what we discussed. Now I think we have time for a couple more questions, if there are any questions. Yes, okay. So, question?
I'll ask you, what safety in your research experience? One is all established so to optimize the fidelity to our system or consistent. It is moving all these details, the limits, the potentials, and maybe the current state of the art teaches. How do you feel about the process of this approach?
When I started working on this 20 years ago, it was just sort of an abstract question. Can we play quantum systems and control the dynamics of quality? But now it has become from a theoretical aspect a very practical question. Because it turns out that nowadays that we do have different parts of the world, different companies, different universities. We have working quantum computers. The point is that scaling up what I said in the beginning turns out to not be possible without optimizing processes. So even the latest results by Guerra, by this company by Michel Looking that I mentioned before, in order for them to do the error correction and so on, they had to use ideas and methods from optimal control to be able for those quantum gates to have a sufficient quality. So from a theoretical aspect, it has become a very practical thing, which means, okay, if I do not use this, I am not able to build a quantum computer beyond just a few qubits. And if I really want to build a bigger quantum computer, I must do that. And this is what allows me to do this. So it is an essential component, an enabling technology, really, which is crucial to making possible to have that stack of quantum hardware to quantum algorithms and quantum software. So that's what is exciting for me, because now there are a lot of experimental groups and companies which are using this in order to make that possible. Okay, so I think that now it's 11 o'clock. So you have existed for 2 hours. I see no one collapsing on the floor, so that's I congratulate all of you on that. So thank you for your attention, and good luck and best wishes for the rest of this school. Thank you. Very good.
Yes, I can send them. Okay, so let's keep it.
Which man you should be?
The third one, how much? Maybe I don't know the people with the the next one, yeah, so big. They should go get the exit. For the ones, you'll appreciate it, cut out the time. Is it better? But I'm thinking about.
And no problem. Long as we get it.
You know, it's not.
Yeah, let me say it, let me do ladies. Usually.
We are doing. Plenty teachers and people kind of start. Yeah, I hear it. I feel like I hear like this. But I hear you not my child. Try to see without the house. Anyone. You want to try it? Hello? Can everybody hear me clearly? This is better. Can you try this? Hello? Can everybody hear me clearly? I guess I'm being recorded. Is this any different? This better. Try the other one. This is better.
Just a small picture. So this is a classical qubit. If you measure a classical qubit, this hammer is a measurement process. You measure qubit. What does it mean to measure? A classical qubit. What does it mean to measure qubit? To see if the computer has zero voltage or 5 voltage. Okay, and that's a measurement. You can measure as many times as you want. You always get the same result. The same if it is a 0 qubit. What happens if you measure a qubit? If you measure a qubit, then only one of the two, the wave function will collapse in only one of the two possibilities. So the result of your measurement can be either 0 or 1. And the probability of getting the percentage probability of getting 1 and 0 is given by the modulus square of this coefficient. Is that clear? Okay, and of course, if the probability has to preserve, then you will get anyway an answer. So the fact that this vector is unitary is very important. It's one of the only important things that you have in your quantum state. Okay, let's go back. Once we say what is the measurement, let's go back with our time state. So what is happening here is that you have two qubits, which are physically separated, but the wave function is unique. You have only one wave function for the two qubits. They're not, even if they are physically separated, the wave function is only one. Okay. So what happens if you measure this qubit here, first qubit? So this is the first qubit, this is the second qubit, this is the first qubit, this is the second qubit. That means the first qubit can be 0 and 1, and also the second qubit can be 0 and 1, but they are very correlated. If you measure the first one and you obtain 0, you know that also the other one is 0 without measuring. Okay. This is what was in the early days of quantum mechanics, what was very uncomfortable for Einstein, because it seems that you transmit something with faster light. One of the qubits can be on Mars, the other can be here. And if I measure the first qubit here, the other one, I know that is 0, even if I didn't measure it. Immediately it will be 0. Okay. Then we can understand that it's true that it seems that there is some. I mean, these concepts are still under development in some way. The interpretation, there are many different interpretations of that. The reason why this is, for instance, compatible with special relativity is that this mechanism, you can think about that during the lunchtime. This mechanism cannot be used for transmitting information from here to Mars faster than light. But it's true that I measured something and I know that on Mars they're reading something, but I cannot actually choose with my measurement if the result of my measurement is 0 and 1. Okay, so I'm measuring this state, but I cannot choose if the result, if the outcome is 0 or 1, because the outcome is probabilistic. So I just know that they will measure the same number as me, but this is not the transmission of information. I cannot do anything. I cannot communicate with them. We just share the same sequence of random number, which is not communicated. Okay, so for going to the, I would need actually also the pen for writing on the whiteboard. Thank you. Okay, before doing that, what I say now has nothing to do with computing. Just, I don't know, mysterious quantum state. What's happening when you add another qubit, when you add a third qubit? How are the states that are possible? How many states are possible? states. So everything. Those states are used are simultaneously in some way explored by the wave function. Okay, through these coefficients. And so one of the advantages of this kind of physical system is that you can represent 2 to the n states. So an exponential number of states according to the number of qubits. Wow, a lot. Okay. And you can also apply an operator on such state, which in one shot is applied to all the states. What is an operator? This is linear algebra. So if the wave function is a vector 2 to the n, the operator acting in this space are matrices 2 to the n by 2 to the n. Okay, you all have a linear algebra in your university course. Okay, so this is the one reason you might think that, okay, this is what is called exponential speed up, quantum parallelism. You can manage many data, exponential number of data. What are the data in this wave function? The data can be, for instance, the coefficient. Okay. But there is a drawback. The drawback is when you measure the wave function, only one of these outcomes will get out of your wave function. So you start with a very simple wave function. Maybe you start with a wave function which has all 0. This is the initialization step. Then you manipulate and build complex wave function with exponential number of coefficients by applying some transformation. And so you can store in some way in principle this system a huge number of numbers of information. Okay. But the drawback is that when you are going to measure the wave function, due to the wave function collapse, you will only have one single series of zeros and one. And it will appear according to the probability of this state. So if I measure this, and this I have like all these coefficients are, let's say, for instance, I have equal probability of getting this. So if I want to see, for instance, how were the coefficients before the measurements, it is not enough just to measure one time. I have to measure several times and try to understand what is the outcome. I find out distributed equally between the states, it means that the coefficients were all the same. So the one problem of quantum computing is that the quantum state, this fantastic state that you can build, is destroyed when you measure it. Okay. And if you want to really know and reconstruct this state, you need to do many measurements and rebuild in the quantum state. Building the quantum state, destroying again, building the quantum state, destroying again. Okay. But I'm almost finished. But I was those writing. Right. Yeah. Yeah, I went right here.
When you are done with the slides, then you write.
Yes. Thank you. Okay, so how you can get some computing out of this? Where remember that quantum computing is initialization, control, and measure. This is the quantum circuit. So each line represents a qubit, and the time evolution of a qubit. Qubit 0, qubit 1, qubit 2, time evolution. Okay. So at the beginning, maybe all qubits are in the 0 state. Let's say all 0, 0, 0, 0, 0. Then you apply some manipulation or matrix. And then you can measure the outcome of the vector. Look at this as a linear algebra problem. You have 1, 0, 0, 0, 0 state, you apply a matrix, which is 2 by n times 2 by n. Okay. And you have a vector. And then you want to get some information out of this vector. And this information is somewhere related to the any computational task. Okay, I'm not telling you how to do that, just to tell you the process. Okay, this information will be related to the computational task, and then you have this drawback that once you measure the state, it's destroyed. So unless you build, so everything depends on this matrix that you apply. And what is the advantage? Let's say, what is the advantage of quantum computing in a very crude way? Is that you can apply matrices that are incredibly big, scale exponentially with the number of qubits. In some way, potentially, you can access to exponential possibility of performing some computation.
You mentioned that the results are opposed to 1 0. So I want to ask all these opportunities will actually
the control is predicting the output, and sensing the output is determined only by the control as a quantum state. So in output, you have a quantum state, you have another wave function. Okay. But then you have the problem that this wave function is not a coefficient of this wave function. So if you want to measure the wave function, then you will see only one part of the wave function, with some probability that depends on the coefficients of the wave function. Okay. Is it clear? More or less. Maybe not, but it's normal that it's not clear. Just ask questions like this one that help me to understand what you are. So, of course, everything. I mean, everything is. What is this control? What is this big matrix? How can we do this? What is the trick? The trick is that here you can use many physical insight, like superposition. You know what is superposition? Superposition is the fact that the wave function is treated as a sum of several different states of an exponential number of several different states. It's a way it's all the states at the same time. Okay. Let me pass this interpretation that I think it's in some way good to images. Interference, wave functions are wave functions. So as any wave function, you can play with interference. And you can have several parts of the wave function interfere. What is interference? Interference is when you have two waves, and sometimes they pop up with bigger intensity and some other with lower intensity, zero intensity. With the quantum state, in order to get higher intensity of the wave function, this specific spot, and this specific spot would represent in some way the answer to your problem. Okay. Let's imagine to have, Yeah, this is actually related to your, I don't know, it's very remarkable, just to say, how you can have a simple use of this. So you mentioned you have an input an image. The image is and 0 and 1. Okay. And then you have here some matrix that recognize some way if this is a cat or not. And then you want to put this information only maybe on one qubit. This is the goal, to concentrate the information on something that you can measure and you have an answer. Not easy at all. There are not many quantum algorithms around. Okay, not many variations, but not many quantum algorithms. Okay, I think I can pass to the, yeah, I can pass to the writing part. Good. I can close. How can I should? Yes. Yes. So sure. Yeah, another question?
So it is
Then
said,
like,
because it has been utilized sufficient measures in order to almost efficient. So what is your, is it, when you say computation capacity or efficient capacity?
On computational assessment, I would be forward on continue. So quantum computers are really and the HR of the community find how to do it, find algorithms, not only algorithms, but also find if you have a problem, okay, whatever it is, you have mathematical description of the problem. And then you find this mathematical description of the problem. And therefore, we can be suitable.
Yes. So you know what they want to use. What is what kind of what kind of study and I think.
Can you very efficient by traffic cards, each card, and some other, no, you need a real computer. Demonstrated that are not tackled like a computer. You don't want and break the division. So this is recreated the scene of that's one of the nice part of one that is capable. This, I think, is one of the major advantages we got so far by quantum computing. Okay, I will not go in the details of which is the state of the quantum computing now, of the large one, when someone else. But in general, well, that's not yet. Now, probably not for it's not sophisticated. But everything is a form of being fast. Okay. So, during your course in quantum mechanics, do you have also introduction to environmentation? Yes. Yes. Okay. As soon as you're lost with this, the advantage of using this is that they are more abstract. Many formula is smaller. Okay, like if you have okay, so this will represent our quantum state. But it is very abstract. It means that you can think this as for our purpose, this is like a vector. Okay, this is just a vector. You can always come back to the vector representation in your mind to be sure that you are you are understanding. Okay, what else to say? I think this is a cat, and then this dual is bra. You can think a cat as like a vector. No, this is a three-dimensional vector, and the bra can be thought as a column vector. Of course, this is not sorry, not normalized. I tried last time, and the pen was able to cancel. Okay. I suppose you have this. Very okay, and then bra corresponding bra. Okay, a row vector. So when you write something like that, you have the scalar product. Okay. This is a vector in a complex space. It's actually C to the n, where n is the number of bits, of qubits, so it's a space. Okay, what else to say? You can represent, of course, if the space is complete, any vector can be represented as by linear combination of basis vector. And then you can also define linear operators, which are vectors which are matrices in this space. So I will what you write now on the okay, another important thing is that related to tensor problems. So if you have a space D, linear space of dimension n, and a W space of dimension m. So this is, you have a CD symbol, tensor product. Yes, someone. Okay. Okay, this is the space, which is a combination of the space. So the vectors, we can write the vectors, so this is quite important. So scroll up and down. I think that okay, I have to do it that. It's fine. Okay, so every vector, so any global vector would be shown like that. And which is the dimension of this new space? Sorry? Yes. So the dimension of this new space is n times m dimensions. Okay. So we can write, for instance, like this. So there will be many notation which is completely equivalent. I just want to write it here. Okay. But this is the same as writing like that. So very often is omitted this. Okay. And this is the same as writing like that. It's always, anyway, a representation of the space with dimension m by n done by the tensor product of the two spaces. Okay. A very simple case. Suppose that we are a four-dimensional space. Suppose that V, so if V and W are two-dimensional vector space, we can define, for instance, a basis in V, which would be 0 and 1, and a basis in W that would be 0 and 1 also. The V times W vector space will have the basis, which is done like that. So is one of the first element is this one, second element is this one. Okay, third element is this one. The fourth element. Okay, so two-dimensional vector space means qubit. Qubit or two-dimensional vector space is coefficient with complex coefficient. Okay, so let's go a bit more in describing the qubits from the mathematical point of view. So we say that a generic state can be written as a linear combination, for instance, of 0 and 1, where alpha and beta belongs to complex number. And the only constraint you have is that alpha squared plus beta squared is equal to 1. Okay, why do we have this constraint? This is the unitary constraint for the state vector, okay, the state of the system. So that when I measure the probability of getting anything is just 1. Okay. So the outcome would be alpha squared with probability. You will get this result when you measure with square probability of alpha, and this result when you measure with square probability of beta. Okay, you can also write the qubit in this way. Cosine divided by 2, 0, plus e to the I times divided by 2. Where theta and phi are real, actually theta belongs to the phi and the phi. Oh. So there is a reduction of dimensionality. Now I will show you what it is. So I'm just saying that this can be, this is a complex number, two complex numbers. So in principle, you have 4 degrees of freedom. Real part, imaginary part for each of the conditions. But you have a constraint. You have a reduction of the degrees of freedom. Here, you have only 2 degrees of freedom. But with the constraint, 4 minus 1 should be 3. Okay? Actually, what's done out is that it's not important the global space factor multiply that by beta for any gate. So E, the I, whatever. Nothing is changed from the measurement point of view. So to represent a qubit, the global phase is not so important. It will be important when you compare two qubits, but not for the single qubit. Okay. Okay, so that means that you can represent your qubit with these two variables, and these two variables can be represented on a sphere. Just draw a sphere. I hope that you can draw a sphere better than me. So here you have the 0. So the 0 represents the north pole, and south pole you have 1 state. What should I do? Should use another color. Okay, this one. And then any point of the sphere, so this is the theta angle, and projected here, you have this phi angle here. So every point of the sphere is x, y, and z. Any point of the sphere represents a state for the qubit. Okay, so this is the so-called block sphere. Who have already seen that or know that? Or okay. Of course, I can lose 95% of the others. Okay. Okay, good. So I think it's fine. So this is the block sphere, and you will see later application to this. When I apply an operator to qubits, we call it operator. We use the term manipulating. We will use the term gate. It means just to change something that is changing the state of the qubit. Okay, and in our case, it would be a matrix. Okay, it would be a matrix. The 2 by 2. 2 by 2 matrix because the qubit has 2 dimensions. And in this matrix, rotate state that we have seen on this surface. It can be rotated around x, can be rotated around y, and so on. Okay. Okay, now we will talk for the next hour, maybe, or something, about these matrices and these gates. These are the operation that we can perform on a single qubit. So, what operation we can do on a single qubit? Okay. Actually, which operation you can do on a single bit? On a single bit, which operation can you do? So, this is a question for everyone except the one. Except the one. Okay. On a single leaf, and just set a relation. Relation means that if it's 0 is 1, if it's 1 is 0. So it's also not operation. Very simple not operation. I'm talking about bit, no? For a bit. For a bit. For a bit, so the title here would be single qubit gate. For bit gates, I have only one gate, not. Okay, the not gate. If I have anything, the negation is this one, and it's going, it has this table of truth. You know the table of truth? Okay, very simple table of truth, 0, 1, 1, 0. Okay, can we have a negation of our quantum bit? Yes. What do you mean? What do you expect out of a negation? I think it's you can have a negation. What does it mean a negation? How one would expect to work a negation of that? That if I have zero state, sorry, if I have the zero state, if I have a zero state, would become one state. If I have the one state, it will become zero state. But this is a matrix now. Okay. So how this would act on a general state? Okay, can one tell me which is the matrix that is doing that? So you have to imagine that zero state is and one are orthogonal states. Okay, so always think in terms of vectors. So this you can see as a vector which is 1, 0, and this you can see as a vector which is 0, 1. Orthogonal state, and the operation that you apply is a matrix. Okay. So which matrix transform this vector in the other and the other way around? This matrix here. Okay, it's like the identity, but the other way around. If you apply it to 1, 0, you will get 0, 1, and the other way. Perfect. Okay, so, but this is only applied to 0 and 1. So we are reproducing from 0 and 1 what the classical bit, the classical knot do. But what's happening when you apply to a generic state? The general state will be alpha 0 plus beta 1. So if you apply X to an alpha beta state, okay, one good thing about quantum operators is that they are linear. So if you know how the operator, this is very important, if you know how the operator acts on the basis set, you know how the operator acts on a generic state, because the action is linear. Okay? Very useful in linear algebra. If you know how your stuff is working on a basis set, you know how it's acting on everything, because it's just acting as a linear operator. Okay, a linear combination of your basis set. You know what I mean? Is it clear that or not? If it's not clear, I can go an example. What is a linear operator? A linear operator is something that acts on a sum. Okay, suppose that this is a vector. This is a vector. It's the sum of coefficient multiplied by the set. And this is like sum alpha I, A, I. Okay. So that's what I mean. If you know how A is acting on the basis set, you know how A is acting on everything. Okay, so we know how A is acting on the basis set because we just defined and we find the matrix, but this matrix can be applied to a general state. And then the state you can do by yourself the calculation, and the state when applied this is exactly this one. So it's just changing the coefficients. Of course, this previous calculation for the particular case where the coefficients are alpha and beta were 0 and 1. Is it clear? Just give me some feedback, maybe. Okay. Then there is another gate, which is the other gates. Where are the gates? Okay, let's see other gates. This is the only gate that we can have for quantum computing. So you see that we have a quantum NOT gate. Okay. But do you have also other gates? Yes. In principle, any matrix can be a gate for a single qubit, but it needs to be one restricted, one requirement, which is very important. That it has to transform unitary vectors into unitary vectors. Okay, so it has just need to be just a rotation in the space, the vector space. So that means that the really only constraint that we have is that A multiplied by A plus is equal to identity. Okay, that means this is the only constraint that an operator has to have. So very often you use actually the word U to use this unitary operation to indicate this unitary matrix. This cross is it means transport plus conjugators. So it's the Hermitian. This cross means U cross means U transpose and then conjugate. Okay. You know that? Yes. Okay. Another matrix that is useful is the Z matrix. Z matrix is made like that. It's 1, 0, 0, minus 1. How Z matrix is acting? Z applied to 0 is equal to 0. And Z applied to 1 is introducing a phase of minus. Okay, so this is the action of the Z matrix. Another thing that you can always do is to represent matrices and operator in this outer product way. I don't know if you have seen this. See that before? I want to introduce some notation, equivalent notation that can be found in algorithmic groups and so on. But when you need them, let's carry on. But back to this you have never seen this notation yet. But this notation is very simple. This is outer product. If you think that this is so this is a vector. This is a vector, okay, and this one is a matrix actually, because if this is the column, say gamma. Let's take a simpler vector like the one that we have here. Let's take, for instance, 0, which is 1, 0. Okay, but 0 like that is 1, 0 row. So when you multiply them, you have something like 1, 0 multiplied 1, 0. And this is like a matrix. This is 1, 0, 0, 0. Okay. And if you do 1, 1, then you have this minus. 1, 1, 1 is this is 0, 1. This is 0, 1. So when you multiply, you get the matrix, which is 0, 0, 0, 1. Okay. So basically, this I wrote as sum of two matrices: 1, 0, 0, 0, minus 0, 0, 0, which is exactly what we have. Okay, this is just another way, compact way to write operators, and as a sum of outer products. And it's nice because it's very compact. I can write this matrix in line instead of in matrix form. Okay, interesting, maybe. Okay, so there is another operator. So you see how many operators you can define. You can define infinite operators, of course. They're not all linearly independent because the matrix has its own, the 2x2 matrix has its own basis set. Okay. Of course, you have 4 elements. So you might define 4 matrices which are orthogonal, and then out of them you can derive all the orthogonal matrices. Another couple of them are missing. One, which remember us that, so the Y gate, remember us that we are in the complex world. So it's 0 minus I 0. Okay. And then actually, and X, Y, and Z gate, together with I, which is identity, they form a complex or complete matrix basis on the basis of which you can build all the other matrices that are unitary. And these are the Pauli matrices. That's Pauli matrices. Okay. There is another matrix which is not related to that, but is very. When I talk matrix now, I will forget about the word matrix and use the same word gate. Okay, just remember that the objective is to act on a qubit. So where you are, there's another gate which is very useful. You will understand why it's useful now, which is the Hadamard gate. The Hadamard gate is done like that. It's 1 over square root of 2, and then it's 1, 1, 1, minus 1. Okay. How this is acting on 0 and 1? H is acting on 0. You can see 0, that means that you have to put here 0, which is 1, 0. And what you will get? You will get 1, and then you will get also as y, you will get 1, and there is the square root of 2. Okay, so this is basically 0 plus 1 divided by square root of 2. Why it is interesting? Because, and it's very useful, because when I find a starting 0 state, which for instance is our starting state in the initialization of our quantum computer, this is acting just having as output a state which is a superposition of 0 and 1 with equal value. Okay, 50-50. This is a 50-50 state of 0 and 1. Then you have H When you apply to 1, also you have a 50-50 state of 0 and 1, but you have a minus sign. That can be useful when you combine together these later on. Okay, all these gates can be seen on the black sphere transformation. There is a link that actually I don't know if I have here, but I just invite you to search for block sphere gate transformation, things like that, and there are interactive outlets that will show you how any gate is applied on the block spheres. And actually the X, Y, and Z gates are like that because they are rotation around X, Y, and Z gates. This is a rotation on an axis which is not one of the principal axes, reference axis. Okay. Yeah, then there are other two gates, which seems not very interesting actually. I will not mention it. Okay, there is the S gate, which you will also will find in on maybe often, which is 100I. And there is the C gate, which is 100E.I. So this is these are the gates. There are many formulas that allow you to write a general gate as a function of others. In particular, you have the so-called rotation gates. Like for instance, the rotation gates along X depends on one parameter, and it's E to the minus I theta by 2 by X. Okay. Okay, but these are, I mean, these are just another way to write unitary matrices. So when you find something like that, it corresponds to the rotation of a certain angle theta variable around the x-axis. Of course, you can write rotation along y and along z. Okay. I think we have finished for the single qubit gate. What about the 2-qubit gates? Which 2-qubit gates? Okay, so 2-qubit gates. 2-qubit. And multiple qubit gates. Try the 2-qubit. Okay, let's first start with the classical gates. Which operation you can perform on 2 bits? What kind of operation you can perform on 2 bits? Or everyone else don't. Okay. Can you in quantum world you will also have an operation which is a controlled knot. Okay, this is an interesting perspective. Let's write the table of knot and of all. Where A, B, 4. Okay, so 0, 0, 0, 1, 1, 0, 1, 1, 0, 1, 1. Then you have, for instance, the end. And of course, is only. So my question is, can I have a quantum gate that describes this logic spot? So a quantum gate is a unitary matrix. Unitary. The unitary is large Just a rotation. I come back with the rotation. Okay, at the light of what I said, do you think that we can, for instance, build something, some gate? So what is the difference between this? Okay, first there is a difference. That the gates are a rotation and they don't change the dimensionality of the space. Here you have a change of dimensionality of the space. You are space is 2 bits and the output is just 1 bit. So of course this operation is not reversible. Okay? Not reversible also because if it was 0, I don't know what it was the previous one. It could be 1, 0, 1, 0. I lost some way the information during the application of the gate. During the application of the gate, if you have a quantum gate, you never lose information. Okay. Let's see what is, for instance, a gate that can have the analog of a quantum gate. It's the XOR. The XOR is A, B, XOR. It's like the OR. Also, the OR is not good. The OR is not good because if it's output is 1, you don't know which one was before. So the XOR is good because it's 0, 0, and then 0, 0, 1, and 1, 1, 0, and then 1, 1, 1, and then 0. So this is one only if it's only one. But this is reversible in some way because of the interaction. I mean, it's not reversible in this form, but it's here I report, for instance, one of the first, because here I am only reporting 1 bit. Also copy one of the 2 others, like for instance this one is out. Like 0, 0, 1, 1. Then, so this is the A. Okay. So you cannot copy. But suppose that here it says out, then you can invert matrix. Or you cannot convert the matrix to have 3 outputs. And you really need to specify a dimensional bit value here. Uncertainty because you have 3 outputs, you cannot come back. Decide which one of the 2 is good. So it's not embedded. But what can we start? 11:10, okay. Okay. So that means that we might have some gate. Actually, the gate that I will show you is the following. Is the so-called controller block. The controller knot is also called the C knot. C knot B. So it's working on a 2 qubit. There is a control qubit, which we call like A, and the target qubit. Right. And the nice thing is that we can define this controller knot based just on the basis set. Because we know that once we have reached this, then all the rest is something. So basically, it can be summarized by this sentence that if control is 1, then target is flipped. What means flipped? Flipped means that X is applied. Okay, X is the knot we have. So what does it mean? That let's see how it's acting on the basis. So I write here like the basis 0, 1. So this is the control, and this is the target qubit. So 0, 1, sorry, 0, 0, 0, 1, 1, 0, 1, 1. So the output say that if control is 1, the target is flipped. So in this case, the control is not 1, so the control is not affected, and the target is not affected. So this is how it acts on 0. Then go to the next. But if the control is 0, the gate is not doing anything on the qubit. Then here is changing because the control is 1, so the target is flipped. That means that we apply X, and since the target is 0, now it has to be 1. And here it's 1, 0. Okay. Okay, this is a kind of generalized XOR, some way. Kind of generalized XOR because here you see that this qubit here is following a similar to the previous truth table. Okay, it's similar to XOR some way. On the second qubit. But of course, all these mechanisms you can just have it in the computational basis. We will call so in principle you can define any basis in your vector space. Okay. In practice, it's very useful to take a basis 0, 1, not a basis which is I don't know 45 degrees rotated. So this will be also referred from now on as computational basis. 1 natural basis set of 0, 0 and 1. Okay, so everything is invertible now because if I know the output, I can know the input. And Okay. Okay, I can just say this. That we can also write this notation. So the action of the store on an AB pair of qubits is to produce A, because the first one is unchanged, and A plus B. What is this plus? This plus means addition modulus 2. Addition modulus 2 is an operation that tells you the parity, basically, of the addition. So, if the addition modulus 2, let's see if it's working. So, 0, 0. That is 0. This one, remember that this one, this one, this one, this one. Okay, this is just 2 bits. So this is 0, and the output is just the sum. Addition 1 2. 0 plus 0 is 0. 0 plus 1 is 1. 1 plus 0 is 1. 1 plus 1 is 2. But when I take the modulus is I don't know the English, the rest. Is the rest in English? What is this kind of divide? Remaining. Thank you. The remaining of the division by 2. Okay. I think good. We're going very fast. So we can just have some other. Okay, let's build our first quantum circuit. So what is a quantum circuit? We have already seen quantum circuit. So when I write something like that, 0, then H, then I use this symbol here. What I mean that I have a qubit initialized with 0. I apply the Adamas state. So it means after the application of the Adamas state, this qubit is superposition 0 plus 1 divided by square root of 2, as we have seen. And then I measure it. Okay. So which is the output of this measurement? Would be 50% 0 and 50% 1, which probably. Okay, let me write this. So here you have also 2 qubits. We have this circuit here. I didn't tell you how the CNOT is represented. CNOT is represented this way. So let's have this. Let's have this state. 0. 0. Then let's see now. Which is the final state. Okay, when you look at the final state, it means the final state of everything. Remember, these are not separated qubits. They are now joined by this gate. So which is the final state? In order to do that, we have to do it by step. So when your X is here, the state would be after the Hadamard here, no? The state would be 0 plus 1 square root of 2 for the first qubit. And the second qubit is 0. Right? This is, let's say, 1. Then what happens here when you apply the CNOT? It happens that second, according to the target, didn't tell you, but this is the target. This is, sorry, this is the control, this is the target. This is the qubit that controls the reaction controls its state. But this is already superposition. So I can think about, since this is already a superposition, this CNOT will act in different ways when the first is 0 and when the first is not when, but on the part, on the component 0 and on the component 1 of the first vector. Okay. So 2 would be, but we don't have to invent anything. We have written before. So we have written what's happening here. So we will use this. We will use this table here. We'll use this table here, so that means that if when the first qubit is 0, it will not be changed the second, and when it's 1, the second will be changed. So if we come back here and we adopt the same, that means that if when the first qubit is 0, I have a state which is 0, and then not difficult to do this calculation, but you can get lost very easily. So I just want to do it in a more clear way for you. So I just rewrite this. I just rewrite in this way. So 0 plus 1 square root of 2, 0. Okay. This is the same way. So this means that there is 0, 0 plus 1 over square root of 2 plus 1, 1. It is the same, but 0. Not very good in writing. And then this you can also, and then you apply the second, apply the second, sorry. Apply the second gauge. The second gauge, what is then the second gauge? Is that when this is 0, this is left like this. Sorry, I use it. Absolutely stop here. Okay. This is 1. This is 0. Okay. Okay. Just a multiplication. So when the first on the first when you apply the CNOT, we can do like that. CNOT. You have something like that. The first is untouched. And the second, well, the second, since the first is 1, the second is flipped. So the second will be 1, 1. So this is the final result, which you can also write like that. Same. Which is one entire state that we have seen before. Okay, so we have used this quantum circuit to build a state which is fully entangled like that. At the end, we have exactly this. This is called the beta 0 state. Is 1 square root of 2, 0, 0, plus 1, 1. So you see how you can build an entire state by applying those Hadamard state and then okay. Just another issue. There are many entangled states. These are Bell states. Beta is 7. Bell state. There are several Bell states that you can build. Actually, it would be a good exercise how to build different Bell states with a quantum circuit. Beta xy are defined as 2 qubit states are defined as 0 y plus or minus 1. So this you can build the one with the plus and the 0. So the beta 0, 0 will be the one with the plus and with the 0, 0. Okay. Let's come back to what I want to do. This is to check the behavior of this circuit here. Sorry? Yeah, sorry. Take all this right into consideration. Yes. Okay. Yes. Yes, right. And we say this, and I give it to you and we send to everyone. Okay. Then let's see this. A, B. Let's see this one. Looks complicated. Okay, have 3 signals, one after the other. The first has distance control, second has distance control, and the other one as control. And the question is, what is the result? Which is the wave function of x? Yeah. Okay, so this is just an exercise to show you this notation of addition modulus 2 is very powerful to manage this. Okay. Why it is very powerful? Because we can write. But we always have to divide by step. So what's happened here? What's happened here? What's happened here? So what's happening after the first? So before you had A and B. Okay. When you apply 1, you have A and A plus B. Okay, we have to find it like that. Then you apply 2. Actually, now the target and the control are in the. So this is the current control. This is the target. So the control is not changed, but now target is changing. So the target is changed A plus the value of the control, which is A plus B. And the control is remaining A plus B. Okay, come right here. This is so for this application, this is now for this was the control, this was the target. This was the target, this was the control. Just by drawing, okay, because of the drawing. Okay. Then, but then this is when you sum the same number modulus 2, you always get 1. Okay. Sorry, you always get 0. Because plus 2 modulus 2, 0. 3 plus 3, 0. Okay. So basically, this can be removed if you don't sum. And so this is B. This is A plus B. Okay. Next step, third step. Now this is the control, the target. And then we have B. Then has A plus B plus B. Okay. This is the A. Okay, one advice, I mean, take advantage of your Now this is the control. This is the target. So to the target, I have to add the control modulus 2. The previous one. From here to here? Okay, so from here to here, why this is the target, this is the control? Just because now it's, synapse is reversing. Okay. Okay. You're right, you're right, you're right. This is not, no, this is one. This is after one. Okay, you mean I put the control and target delayed? Yes, I understand. Thank you for pointing out. So I brought the controlling and target actually to the after the state, after the application, not before the application. Correct. So sorry. So it's just thank you for pointing out. So the control and target, if I apply this, the control and target are this one. Okay, so this is control and this is target. Okay, now all the algebra is fine, but I just wrote CNT after applying the gate. I should have written before applying it. Control and T, and now this is T and this is C. And now this is now this is the C and this is okay. That is the same, T and T. Okay. So this is the result of the application, and then from here to here, just sum 2 times A. So 2 times A is 1. And A plus B. This is going to become B. Okay. Thank you. I like this interaction. Don't be shy. Okay. Thank you. But then, how do we interpret the result? What is the result? So at the end, you have just split them, right? So you have that here you have B and here you have A. So the effect of 3 consecutive T-nodes made like that is just to exchange the 2 qubit values. This called swap. It's just a swap. Okay, is it swapping the 2 states? Okay, you see that we have built a quite complex, quite interesting new gate that is just exchanging the 2 qubits just by applying several times the basic CNOT. Okay, so in general there is you know that there is a theory in classical computation that says that all the ports can be built by single ports, right? So everything can be built by a single port by using only NAND, not AND. If you have not AND, you can build all the computers that you want. Of course, it should be better imposing more on this one on the other. So the same applies in quantum computing. You can, if you have CNOT and single qubit gates, you can build all the all the gates. What do you mean all the gates? It means that now we are referring to only two qubits. But in principle, you might have many qubits. And then you might have big operation and then the output. Okay, so the only requirement is that this is a unitary operation. And you can always decompose this unitary operation using CNOTs and two qubits distance. So today you know everything you need to know to build any kind of gate of whatever number of qubits you want. Okay, I think maybe we can finish with this and then another important issue and difference between classical and quantum computing is the following. Can we make the break now? Actually, you are tired. But the organizer is saying the organizer are not here, so we cannot decide. Let's go on. Yeah, it's very quick. It's just the no cloning theorem. The statement like that. It is not possible. It's another strange law. Not possible. To create an identical copy of an unknown quantum state. I don't know why it is not working. Kind of style it looks. Okay, what does it mean? That if I have a quantum state, I mean, if I have a classical state, in a quantum calculation, bad. Okay, that's bad. You can do other things. So we can show this how this is possible. We can think we can suppose that this is possible, and then realize that this is possible only in very few states, specific states, not in general. So let's suppose that you have an initial state made by psi and S states. So there are two qubits, unknown qubits. And you have a unitary transformation that is possible to do what we say. So when this unitary is applied to psi S state, then it's producing psi and again psi. So that means we can use this unitary for two different wave factors, copy two different wave factors. We can also use unitary. Okay, this. So that means that we can also use unitary to copy another state. Always this as a state, as initial state. Okay. Then we can make the scalar product of these two vectors. These are two vectors. This, that can be written like this and this. So the scalar product would consist in taking this, having a bra, that means like that, actually the second one, having the second bra, and cross. So this is the bra. Of course, when you have the bra, you are going to apply the cross operation, that means we can transpose the matrix and to change it, let it act on the other way. So this is 2. This is 5. This is 6. But this is unitary. This is 1. So what you get at the end is that S multiplied by S, this is 1. And this is the scalar product between phi and psi. Okay. But if you do the scalar product of these two, what do you get? You get phi psi modulus squared. So this is phi psi, but it's also phi psi modulus squared because of this. But this because of what we have seen here, and this because of this. Okay, but here you have like one unknown value, which is the scalar product between phi and psi. This unknown value is can be called as x. But here you have like an equation like x is equal to x squared. So that means the solution at x equals 0 or x equals 1. X equals 0 means that the scalar product is 0. So that means that phi and psi are orthogonal. X is 1 means that phi and psi are the same. So basically, only you can copy only if the states that you're copying are orthogonal to each other. Then you make a copy. But it's a very special case. So you cannot copy two states that you don't know what they are. In some way, could we know this before? Look at what this is doing, what this unitary is doing. It's transforming this into this. Is there a way to come back? I lost every information on S. So there's no way to come back in some way. No. Conceptually, we say that everything has to be invertible. So the only way to come back is that some assumption between phi and psi. Like for instance, S is perpendicular, then I can reconstruct it, or S is the same as psi, and then I can reconstruct it. Okay, I think we can stop here and having lunch. Thank you.
For outside, I have these two here. The second. This is different. And we just like this. This one, the second one. And then I need the same. The one you do the same is your values. Okay. One. So you're right to the conclusion that some true if x, which is the character vector, 0 or 1. Think that you can do that, but only if the two vectors are orthogonal or orthogonal. So 0 means they are orthogonal. Okay, that's not that 0, 1 or they are orthogonal. So they are orthogonal or they are 1. Yes. And this is because of what we said before, the loss of information. You are be able to come back. So if you know that they are the same, you can come back. If you know they are orthogonal, also you can come back. You can see S or so about or according to the case, you can come back. Doesn't exist yet. Unitary, This to the. Yes. Okay.
Or. It's just looking at something.
I changed it because I was assigning control and time after shift. So what you have. Much before. Now, yeah. What my insurance. What should come? I want on seven. This is the thing, because I didn't do anything from here to here. I just somehow page was edited, but I know. Actually, let me write.
just want to say this.
What you get here.
Can you send me back? I created that, let's see. I was able to save the notes.
The one you get is. The one you get is.
Yes. This is called the, we don't need the one. Can you send it? Okay, you're already safe.
Okay.
So it's this.
I think also I say we did that.
So,
I said, yeah, check the destination documents.
So I remember.
I'll send it.
You can copy it. Do I get your mail from?
Just one thing. So there is lunches here
Yes.
over there. Okay.
I'm coming with you. My name, the mail.
I'm gonna read on new section.
That's
Okay.
She said she wants to ask a question.
And in this part, I have A with this B. Yeah, you have. Then
Yeah.
I'll maintain A, then A with this B will be A.
Yes.
Then here, the B becomes the control
Yes. This is one. So A plus B and
B.
this. B.
B.
Yeah.
Then here A becomes the control, so I maintain the A here.
Okay.
And I
So just
control
change
the
it
B.
to very something like that. And for sending all the time.
A plus B.
Is the I away lowercase or uppercase? The I.
We don't. It's not fine. It's like we don't.
Oh, okay. But no, the beginning. Is it I or
L.
lowercase, right?
Yeah.
What's up?
Yeah, we can.
This is
So this is one. This is zero.
Because whatever is what is
So this is just B, and then B plus B is zero, and this is B.
Okay.
The last. Lápájá ní bẹ̀rẹ̀, ká túbọ̀ bí ti nǹkan. Ká túbọ̀ bí ti nǹkan tó bá ń jọba. Àwọn ẹ̀ ẹ̀ inú ẹ̀ tí ní ẹ̀ ń pẹ̀, àmì ẹ̀mẹ́ méjì ní ìpè náà. Nínú ìṣèwọ̀ yìí sẹ́. No, gracias por accesar. Sí, entonces, and also they keep the anti-retardants up to 7. Usually, I do so it's good.
يا جماعة. You can raise it, okay.
Private. Okay. The Zoom is still running, right? Well, you see this one, so can we play it? That one is not funny. So can we play it since you saved it? Only funny. 0.6. I have it. So you import it carefully. My yield should be. The world needs like this. I feel like when you have plans.ถ้าของความเห็นออกไปวันออก
That's why kids were, it's awesome. That's why you see, it's easy to allow this one to break up and cross the lines of the world. That's sick for that. Take it to so really catch it. Don't you this better next 6 years for people. If you don't change our schools, you must be things that this gets while it's cheap, the still working on that, it's still elsewhere. While you miss your
With you still running the
You're still doing, but like, cheap, we do not much that way, but it's Brian Chavez. It's like a shoe, you can go with a. It's the best possible.
Now should the blank white, if I don't want to write here. Yeah, so open somewhere. Open maybe paint, something like paint for him as blanks, then we shape put open. No, he just switch. Yeah, when you switch, so share entire screen, you get it. Don't write inside it. No. Also plain. I will just switch between. Okay, then why didn't you? You need everything. You put the plain one with the open the sound. Yes. Yeah, that would be better. Well, you didn't copy it from them. Yes. Over them. Hold on. You can write here. Yes, you can do that. Sorry, let's see how they would see it from here. You can write here, but it's not that big. Is that okay, or you want the biggest? No, let's read how you want. So she's switching. Okay. Just create the layout. Maybe have. Okay. Then you have your this one slide. Another. Yes, new year. So right now, that's right. This is the first one. The money.
or you learn also more efficient.
You see, I want to this machine is you show how you actually they improve this way. Well, I like create for us, I use like searching. I just want to get this one. I have a study is if I'm writing code from scratch, because I think it was yeah, it's not a personal and it's the project. And it's because I studied so much, especially in university studies. So I made like knowledge and skills. I think I used to be just with somebody else. This seven goal, and I need to the problem for me. I have also the less games and quicker. But I see the team.
It's not touch screen. I can use this one. Okay, I have to use the one. Hello. Audible in the background.
Hello, everyone. We are starting the next session now. Everything.
Good afternoon. So yeah, this is the post lunch session, so everybody is a bit sleepy. Let's start a bit. So in this tutorial, I will be introducing to you not exactly quantum computing, but what quantum computing is used for mainly is solving chemistry problems. And for that, we need some basic concepts, which is always useful when you want to apply quantum computing to quantum chemistry. So the first, in the part one, I will be introducing the most basic concept in solving many electronic systems, which is Hartree-Fock theory. And so these are some books that I would recommend you. You can find PDFs of this online very easily. And so one is Molecular Quantum Mechanics by Peter Atkins and Quantum Chemistry by Levine. Very good books with very clear conceptual understandings. And so I will start. I will not use the slides entirely. I will also derive the Hartree-Fock equations and how to solve the Hartree-Fock equations on whiteboard. And so I will first introduce what is quantum chemistry. Then I will state what is what are the approximations that we need to solve for a multi-electronic molecular system, which is the Hartree-Fock approximation. Then I will derive the mathematics behind it. So basically, quantum chemistry tries to solve, it tries to apply quantum mechanics for chemical systems. And chemical systems have a nucleus and a number of electrons in it. So as if we kind of recap on what we know in from the basic postulates of quantum mechanics and its application, we can see that so, so what we are trying to solve is we want to solve the main electron state. So what quantum mechanics, if we kind of recap the quantum mechanics, what it can actually solve exactly without an approximations is only the one electron problem. And what it does is for the one electron problem, the potential we have a proton fixed at the origin, and it has, say, we have a proton with mass, say, mu, and it is bound by a potential due to the attraction with the electron, which is given by where this r is the distance between the nucleus and the electron. And there's another energy that is in the Hamiltonian of this one electron system, which is the kinetic energy. And this is basically just the second order derivative square. So this is the expression of kinetic energy in the form of and after so what we do is by quantum mechanics we solve the Schrodinger equation. Which takes the form, very simple form. If we reduce it from the, if we reduce the coordinates into a spherical form, it gives. So I'm just recapping this term going through this quickly. And after solving it, you get the solution of the wave function of a one electron system. So if we just assume that what is this? So the first term is the radial component of the wave function. The second terms are the angular momentum. the spin angular momentum and the spatial angular momentum of the system. And the one unit, so what this essentially is, this is the solution of a one electron wave function. And this is what we call this as an orbital. This is the definition of orbital. You may have heard about orbitals when you deal with chemistry. So orbitals are, since one electron is an atom, these are basically atomic orbitals. Okay. So now, what we want to do is basically this is the thing that can be exactly solved by quantum mechanics. This is the exact analytical solution, but once we go to the multi-electron system, there's an extra repulsion, there's an extra potential that comes in the picture, because now we don't have just the electrostatic attraction between a nucleus and the electron. We also have repulsion between two electrons. So whenever there is more than one electron, we have repulsion terms between the electrons, and the Hamiltonian then becomes. So maybe I can just show here. Yes. So this is the Hamiltonian for multi-electronic system. So you can see that in addition to what we had for a one electron system, we have two new terms. So we have nuclear repulsion, because now there are two nuclears for two atoms, say. And we have this B, which is inter-electron repulsion term. And since this is a kind of two-body interaction, and thus we cannot separate this into like one electron terms separately. It cannot be written as a product of one electrons, and thus there is no separation of variables in the Hamiltonian. And if we cannot separate the variables, quantum mechanics cannot solve it exactly, which is why we need to have some approximations in order to solve the multi-electron system. So now, what usually is done for quantum chemistry is we assume that the nucleus is always traveling very slow in comparison to the speed of electrons. That is what is called the Born-Oppenheimer approximation. And that is what the Born-Oppenheimer approximation is. So the electronic and nuclear coordinates, they are treated independently. That is the nucleus and electrons. The wave functions of the electron and nucleus can be treated separately. So if we impose the Born-Oppenheimer approximation that the nucleus and electron do not affect each other, then the Hamiltonian becomes very simple, which is so this is a Schrodinger equation for multi-electronic system. So now we have, this is the kinetic energy of each electron, the nuclear repulsion, the nuclear energy attraction, which was there even for the one electron case, which can be solved exactly. And this term, this is the culprit for which we cannot apply quantum mechanics exactly, and we need approximation. So what we need now is an approximation for this phi k, that is the wave function of a multi-electron system. And that is what Hartree-Fock theory, Hartree and Fock together,
proposed and they solved, and it was very successfully done. So after we get a correct wave function, we then have to solve the energy of the multi-electronic system, which is just an expectation value of the wave function with respect to the Hamiltonian, this Hamiltonian. And then we minimize it, variation T, and we get the energy of the molecule that we want to calculate. So the Hartree-Fock theory was originally developed by Hartree and Fock around 1927 to 1930. And if you remember from the quantum mechanics that there is antisymmetry present in any electronic wave function, which is caused by the Pauli exclusion principle, and which states basically that the Pauli exclusion principle it is the basis of any fermionic wave function, because fermions, so fermions means where the particles are the spin angular momentum is half, and any fermionic system will have antisymmetry. And what does antisymmetry mean? So antisymmetry basically means that if you say you have a wave function psi r, which is dependent on the coordinates of the electrons. Say you have you have two electrons, so you will have two coordinates. Ri or J. Where Ij are the electron coordinates. So if there is antisymmetry, if we exchange the position of these electrons, then we'll have a negative sign imposed here. So when we exchange the coordinates of the electrons, if it's a fermionic wave function, so it will have antisymmetry and will have a negative sign. So what this basically means, the consequence of this Pauli exclusion principle is that no two electrons can occupy the same spatial orbital. So I just introduced the orbital. So orbital always has spatial coordinate dependence. So two electrons can never occupy the same coordinate, the same spatial coordinate in a wave function. And this is the fundamental characteristic that any wave function has to respect. So if you want to approximate for a solution for a multi-electronic system, you need to respect the antisymmetry condition. So that's what Hartree and Fock had to figure out first. Yeah. Yes. Okay. Sorry. No, I was just introducing the thing. Okay, and if you have any questions, please ask. You can interrupt me anytime. Are there any questions now? So. Okay, so just to summarize what I said, Hartree-Fock wave function is a way to approximate the wave function of a multi-electronic system. This is the Hamiltonian is given by, as I said, so this is the Hamiltonian of a multi-electronic system. There's a one electron operator. There's the kinetic energy, the first one. The second one is the attraction between a nucleus and the electron. So the first two terms is common with what we had in a one electron system. The last term is the one that is addition. That is repulsion between two electrons, because both electrons are negatively charged, so they will repel each other. And this is what we call the Coulomb repulsion term. And this is the whole electronic Hamiltonian. Okay, so now back to the antisymmetry. So this is what Hartree and Fock had defined as the wave function for a multi-electron, and how they got it is, let me just. So basically, what Hartree defined the wave function as a Hartree product. So what he basically proposed is very simple. Since we can solve the one electron problem exactly by quantum mechanics, what he proposed is that we just, for a multi-electron system, we just take the products of each one electron wave function that we can get from quantum mechanics directly. So say we have an n electron system. And the solution of each one electron problem, we call it chi. So for n electron system, there are so what these chi's are? These chi's are basically the one electron wave functions that we can get by solving using quantum mechanics directly. So these are basically these wave functions. So using quantum mechanics for one electron problem, we get the wave function in the form of orbital. And what Hartree said, that we just define the wave function of a multi-electron as psi n equal to just product of each. So this is what is called the Hartree product. This is very simple. So we just take a direct product of each of the wave function, and he has told that this is the wave function we can assume. But what is missing from here is the Pauli exclusion principle, which has to be respected for any fundamental wave function. So for Pauli exclusion principle, we need antisymmetry, and for antisymmetry, what we need is if we exchange any of these So to impose antisymmetry, what we need is the wave function should be the psi n should be such that if we exchange any of the electrons, say we are putting the electron 2 in chi1, that is the spatial component of 1, and put 1 in 2, it should be such that psi n, say I'm calling it psi n prime, should be minus of psi n. But a simple product of all the one electron wave functions does not respect this. So what we have to ensure is we have to ensure the antisymmetry, and for that we need we have to antisymmetrize this wave function. So let me antisymmetrize. So we need an antisymmetrize operator so that this, if we apply antisymmetrizer upon this Hartree product wave function, that is the product of one electron wave function, it will produce a new wave function which respects this Pauli exclusion principle. So what we have to do, the operator can be defined as sum of all permutations between the electrons. So we're exchanging all possible permutations, that is, we are placing electron 1. We can put electron 1 here, we can put electron 1 anywhere, and so it has all the possible permutations along with a sign. And this is the permutation operator. So according to Pauli principle, whenever we exchange electrons between spatial coordinates, a negative sign is imposed. And if we apply this antisymmetrizer onto the Hartree, say I'm calling this Hartree product. Lights on the Hartree product wave function. That is the product wave function of one electron on grid. If you apply this operator, antisymmetrize it, we get like we have a determinant where the rows are electron 1 in electron 1 in all possible spatial coordinates. So we put electron 1 in orbital one, orbital two, up to orbital n. You can put it anywhere, and the columns will represent the spatial coordinates. So we have chi1, 2, up to chi n. Sorry. Chi1. If you look at this structure closely, and if we expand the determinant, you will now see the kind of magic that happened. So if you expand this, so as I was saying, so Slater, so the after antisymmetrizing the Hartree product, we get a determinantal form where the row corresponds to putting electron in each of the possible spatial orbitals, and the column represents putting in the same space each orbital. And what is the well, to just simplify what this means basically is, say for instead of n electrons, let me just show a simple example for 2 electrons. So 2 electrons, the wave function will be just R1 and R2 here. And the antisymmetrized Hartree product will be phi 1 R1, phi 2 R1 in the row, and another row will be phi 1 R2, phi 2 R2. If we expand this determinant, you will see that it becomes the factor, the one by n factorial is basically just a normalization factor of the wave function. So the normalization means basically you take the square of the wave function and divide it by the no, I mean this is the square of the wave function, and divide the whole wave function by it to normalize it, so that psi becomes 1. So leaving the normalization factor out, so after expanding the determinant, we get phi 1 R1 into phi 2 R2 minus phi 2 R1 phi 1 R2. So we're basically just opening the determinant up and looking at what is. So this is the antisymmetrized wave function for a 2 electron system. Now if you kind of contrast it with what Hartree had first proposed, that is the Hartree product. If you exchange electrons 1 and 2 in this wave function, you will see that it becomes electron system. The anti-symmetrized wave function. So I'm calling wave function as just in a shorthand note, WF. It's 1/2 chi 1 chi 2 chi 1 2 chi 2. So this is just expanding the determinant. We are finding the value of the jitter. So the interesting thing after anti-symmetrizing, as expected, we have to just check if the Pauli principle is valid here. So we just check that. So we interchange 1 and 2 electrons in the spatial orbital. So what if we interchange 1 and 2? Electron 1 and 2. We get is chi 1 2 chi 2 1 minus chi 1 1 chi 2. So what we do is very simple. Just you replace 1 with 2 in this wave function. So it becomes 1/2. You in the first one it's chi 1 1 chi 2. So when you interchange 1 and 2, it becomes chi 1 2 chi 1 1. And the second one becomes from chi 1 2 chi 1 to chi 1 1 chi 2. So if we now see this is basically this is equal to, if we call this is chi 1 and this is chi 1 line. You'll see that this is basically nothing but minus of psi 1. If you put a negative sign in psi 1, you will get psi 1 prime. So what this basically shows us that our anti-symmetrizer operator works very correctly, and the Pauli principle is satisfied. So now we have a satisfactory wave function for the multi-electron system, where both the antisymmetry and also the multi-electronic nature of the wave function is respected. And now we can use this Slater determinant structure we can use this structure of the wave function as our guess wave function for a multi-electron system. And then we try to solve the Schrodinger equation using this wave function with the many electron Hamiltonian. This one, the many electron Hamiltonian, the molecular Hamiltonian. We plug in our wave function here, we solve the energy, and we try to find the energy for a multi-electron system. So now that we have the wave function, let us just. Okay, so a few just comments on Slater determinant just to summarize, and please ask me any question if you have. So the many electron Schrodinger equation is complex because we cannot solve it exactly using quantum mechanics due to the electron repulsion, Coulomb repulsion, which makes it impossible to solve directly because we cannot separate the variables, the electronic wave function variables, for any system which has more than one electron. So we have to approximate a wave function for the Hartree-Fock in the Hartree-Fock method. And what Hartree-Fock suggested is we treat the total wave function of the multi-electron system as just a product of our one electron orbitals, which are exactly solvable by quantum mechanics. And then we impose the Pauli exclusion principle, and we finally get determinantal structure of the wave function. So basically, each of this determinant is a possible wave function for a multi-electron system, but we still need to find what is the best occupancy of the electrons here. So for that, we have to just plug it in the Schrodinger equation and calculate the energy. Whatever minimizes the energy of the system will be our Hartree-Fock energy. Okay, so you can get the Hamiltonian, the kinetic energy term is the first one. It's just a double derivative. The second one is the repulsion, the attraction between the nucleus and the electrons. And the last one is the electron repulsion term. We have the Slater determinant. We now try to find the best wave function that can be possible from this one by using the variation principle. Now, you might have learned in quantum mechanics the variation principle, which states that if you have any approximate wave function, if you kind of take this expectation value with respect to operators, then it is always greater than the true energy of the exact wave function. So since we cannot solve exactly a multi-electronic system and we're approximating it, so by variation principle, the energy that we get using this approximate function, that is the Hartree-Fock theory energy, will always be greater than or equal to the exact energy, that is easy. Just it's okay. And another thing that we need to have is we have to respect the orthonormality of the orbitals. So what does that mean? That a direct or a tensor product of two separate wave functions that we had taken, that since this is a product of one electron orbitals, we have to ensure that the direct product of each one electron orbital is also orthogonal to each other. So basically, phi I phi j del I is equal to Kronecker delta ij. This means that if I equal to j, it's 1, and if I not equal to j, it's 0. So that is another constraint that we have to impose while solving the Hartree-Fock equation. Now, what we need to do, as I said, we have to plug in this approximate wave function and compute the expectation value of the approximate wave function with respect to Hamiltonian. To do this, what we need is a systematic way of finding the expectation value of each piece of the Hamiltonian term with respect to the orbitals. Here I have just summarized this on Slater rules. This is called the Slater quantum rules, which relates the expectation value of a Hamiltonian term with respect to a wave function. Let's just show you what it actually means. So we have to solve the Hartree-Fock wave function. The expectation value of the Hamiltonian with respect to the approximated wave function, which Hartree-Fock, the antisymetry is Hartree-Fock wave function. This will give us the energy of the molecule at this approximation. So this is the energy of the multi-electron system. Now just getting into how to find the expectation value. So the Hamiltonian, as I said, has a kinetic energy term plus nuclear electron attraction plus the electron repulsion. The first two terms are you can call them as one body operators because they depend on only one electron at a time. And this one is the two-body term, and this is the culprit for which we cannot solve it exactly using laws of quantum mechanics. This is two-body operator. By body, here by body means electrons, basically. So maybe it's better, it's less confusing if I call it one electron operator, two electron. Okay. So when we have to find the expectation value of any approximate wave function for Hamiltonian, we first need to understand, say I'm calling this H1. Plus H2. So one electron term and two electrons. So we are clubbing these two together and calling it H1. And this one as H2. to find the expectation value. We now have two pieces of expectation values that we have to compute. One is the expectation value with respect to the one electron operator. Plus. So how to find this value? That is where Slater-Condon rule comes into the picture. So what does to solve this to get the expectation values? Slater-Condon. I'll just state the rules here without deriving how they came, but you can find the derivations in any of the books that I mentioned. So what this rule state is that so to show results here. Yeah, so what the Slater-Condon rules say, basically for the one electron part of the Hamiltonian, the matrix element or the expectation value between two Slater determinants, which differ by only one orbital, but are otherwise identical. What that means is so see we have two wave functions, psi1, psi2. This has a structure. So this notation is basically equivalent to determinantal. So this basically means if we just recap what we did. Psi11, Psi21 to Psi1. So this is a shorthand representation, which presents as determinantal structure. Psi11, Psi12. Okay, since we're doing a 3-electron example here, we can write it exactly without any dots. So this not this notation, which is called bracket notation. So this whole Slater determinant can be summed up as using this notation. So we say we have two wave function, two Slater determinants with us. One has this structure and the other has psi 1, 1, psi 2. Instead of 3, electron 3, we have an electron 4. It's a dummy index, so we can just put 4. So what the Slater root state is, if we have two Slater determinants like this, then psi 1 H1 psi 2 is equal to the orbitals by which the two determinants differ. So for example, it becomes okay. So this notation has become a bit confusing. So I should not call this psi, maybe I call this phi. Because you have to have some distinction between basis wave functions on which the multi-electron wave function is constructed. So since I'm calling one electron wave function to psi, I'm calling this as phi. So, phi 1, phi 2. Now we see that these two wave functions differ by only one coordinate. That is the last one, the psi 3. The electron in psi 3 is different in between phi 1 and phi 2. So by Slater roots, this will be equivalent to psi 3 H1 psi 3. So the rest of the part which are same, they just vanish. So this simplifies the equation we want. So from three wave function product, we come down to just one. So it's a one electron wave function expectation value. So that's what Slater rules basically help us. So it reduces the multi-electron expectation value to a sum of one electron expectation values. So to sum up, we have, if we have a matrix element of one body Hamiltonian between two separate determinants which differ by only one orbital, but the rest of the part of the determinant is identical. It reduces to a sum of all the orbitals. I mean, this is a sum of all one electron expectation values of the orbital. And if the two Slater determinants differ by a single electron in a single orbital, then the off diagonal say I'm not using the say little mistake here. So this is fine. Yeah, so if we have two Slater determinants differing in one orbital only, then the expectation value of the diagonal element of the Slater determinant basis is just reduces to a sum of all sum of all one electron wave functions. And the off diagonal element is 5.81. Right, it's not a sum now, it's only So to summarize this part, reaction of a one electron Hamiltonian, the expectation value. So we have Slater rule. For matrix element. Between the two determinants. Between two determinants which differ by one orbital only. Diagonal element, that is say I'm equal to psi I H1 psi I is equal to J so psi here is a multi-electron Slater determinant, while the phi's are one electron orbitals. So how does this simplify our calculation? I mean, with the computation of our Hamiltonian expectation value, because these are already exactly calculable. Because by quantum mechanics, we can solve the one electron orbital exactly, so we can get the integrals with respect to the Hamiltonian exactly from we can calculate them exactly by analytic solutions. Exactly solvable. These values we can get exactly. Similarly, the off diagonal that is one SII, SIG. Since we already, in this example, since we already said that the two determinants differ by only one orbital, this value will be equal to just the one electron orbital by which the two size differ. Again, this is exactly available from the quantum mechanics calculations. Okay, so yeah, that's this is the summarization that, which I just now said that, so diagonal element is equal to the sum of all expectation values with respect to one electron orbital, and the off diagonal element is just one term. So it's the orbital by which the orbitals by which the two wave functions, the two Slater determinants differ. So if it differs, say one of the Slater determinant has the orbital I, and the other one doesn't, the other one has J in it, so the expectation value will be phi I H1 phi J. And if it differs by more than one orbital, the matrix element is zero. Because this is just a one body operator, it cannot connect to Slater determinants which differs by more than one orbital. So for the one electron operator part of the Hamiltonian, these three are the Slater rules. For the two electron part of the Hamiltonian, between two Slater determinants. So the diagonal term of the Slater determinants is equal to a sum over all the orbitals. The first term, this is called a Coulomb term, because you can see that the ordering of the one electron orbitals are the same. So phi I phi j, H2 phi I phi j. And the second term is the exchange term, because here the ordering of the orbitals, you can see the spatial orbitals are being interchanged. So it's phi I phi j, H2 phi j phi I. So now that we can decompose the expectation values of from a Slater determinant to the one electron basis, it will be easier now to solve for the Hartree-Fock energy. And if I directly go to using directly the results from using Slater Condon rules, now we can decompose the value. In So these are basically matrix elements between orbitals. And this was matrix immediately, whole letter determinant. So we reduce a multi-electron wave function into a sum of one electron expectation values. So this is what we wanted originally, because if this was possible naturally, then quantum mechanics would have been able to solve it. But using this approximation of Artifacts, now we are able to decompose this into one electron functions, each function, and now we can proceed from the Schrodinger equation, that is H psi equal to E psi. So let's get directly into the solution of the Schrodinger equation using this later rules that we just saw. So if you plug in now, so this is the n electron wave function, so n equal to number of electrons. Using the Slater rules, we have what was I calling the one electron functions? Phi. So it becomes phi 1. So by one I mean one electron operator. So I'm directly just taking the expressions that I just showed. So one body operator terms reduces to sum over the diagonal term is sum over I phi I H I phi, and that for the two electron term is phi I phi j h to phi I phi j minus phi I phi j h to phi j phi I. So we have phi I phi j 1 by R12. This is the repulsion operator of the two electron repulsion operator. Phi I phi j minus R for simplicity, what is usually done is we don't write the electronic coordinates. We just concentrate on the orbitals. So maybe that will make it a bit cleaner. Phi I phi j. On by R. Minus the exchange term. Okay. So this is what we get directly from the Slater rules, where we have now using Slater rules, we have successfully reduced the expectation value of multi-electron any electron wave function to sum and sum of pieces of one electron wave functions. So when you solve for any quantum chemistry method, you will find the terms when you solve Hartree-Fock, you will see that you are getting integrals, Hamiltonian integrals. This is what is called one body Hamiltonian integral. These values you get directly from any quantum chemistry or quantum chemistry software. And these pieces are what is used when you apply quantum computing to quantum chemical problems. So you just get this integrals, and these together are two body. So it's the same thing, it's just in a printed format. Hartree-Fock phi I h phi I plus the term which is called the Coulomb integral term, the Coulomb repulsion, and this is the exchange repulsion. This is what is special, and also it's not explainable classically. This arises due to the imposition of Pauli exclusion principle in a fermionic electron wave function. So the one electron Hamiltonian, so the one body integral. So it's the sum of all one electron energies for each orbital. The second term is the Coulomb interaction, which is the repulsion that each electron feels in each electron's presence. The last term is what arises due to the antisymmetry of the fermionic wave function. So what is usually done to give it a more simpler structure as you can see that the first term has a single sum, a sum over only one variable I. And the second term, since it's a two-body term, it has a sum over two coordinates, I and j. To simplify the equation, I will show you why we need to simplify it. We can define a new operator, which is called dot operator, which we define as h plus a single sum j equal to 1, j minus k, where j is the Coulomb operator and k is the exchange operator. So essentially, what this does is this reduces to define a new operator, the top operator. This small h is equivalent to one body and new operator. J is one where we had phi I, phi j, 1 by r. Coulomb repulsion between electrons. And this is the one where the positions of the orbitals are interchanged. Fine. I'll just finish with this again. So essentially, what the definition of this new operator, what this helps is we can cast the Schrodinger equation that we had defined earlier. The H psi equal to P psi, you can write it directly in the form of just one coordinate now. So it's basically if you define this, we get This simplifies the equation, the Hartree-Fock equation that we are solving, the Schrodinger equation, to just one coordinate, and this is much easier to solve than when we have multiple indices here. Like this is easier to solve than this equation here, where we have one coordinate, sum over one coordinate and two coordinates in the second term. So this is basically a pseudo eigenvalue equation. Why is this pseudo eigenvalue? Because the operator here that we have the form, this has it is the two-body term is hidden within the Fock operator. So it's not an exact eigenvalue equation. It's called a pseudo eigenvalue equation. And if we solve this equation using any diagonalization method, we can get directly the energy of the multi-electron system. So the F here is a Fock operator, the phi I are the one electron orbitals. Epsilon that we get after diagonalizing this Fock matrix is the corresponding energy of each of the one electron wave function that we have taken in the Slater determinant wave function. So I should end here because the time is up, and I will continue tomorrow from the consequences that we can get from the Hartree-Fock equations. Which is just to So I will just mention some of the consequences that we get from this by solving the Hartree-Fock equation and its applications in chemistry and physics, and then move on to how can we, what are the limitations of Hartree-Fock and how can we get rid of the limitations and go beyond Hartree-Fock theory to improve the energy of a multi-electronic wave function. Thank you. Receive.
You want to?
No, I mean, for the, okay. Or I will also give them the lecture notes.
Okay.
Okay.
Yes. Yeah.
Yes.
Which of the
Speakers.
speakers? That's sorry, because I really, when I sit here at home.
Why?
I think what.
Yes, so that's it.
Okay, I just picture loud this.
But the best question, we just hear what's now with the mic. Yes. Let's see. Next slide, there, right? What's really important?
After that, I think.
Yes. Oh, no, but you can say one in the morning, it's fine. Okay.
So you can say this.
Yes, exactly. No, exactly.
Yeah.
Is the mic working?
Yeah.
Hello, everyone. Hi. It's been a long day. Yeah, so we have one more round of lecture before we close. And whilst you are waiting for our professor to get ready, I want us to do a little activity. So if we could all be on our feet, stand up, because you need energy for the last lap. So please stand up if you can. Everybody stand up. We are going to do a simple stretching exercise. Some of you are at the end of your energy, at the end of the week, but you need extra. So last day. Some of you are not speaking to any other person, okay, just those you know. So please find someone that you don't know, or you're not talking to since the conference that started. Find one person. You're not talking to you. Find one person that you don't know or you don't know their name. You're not talking to them since the conference started. One of the key aspects of conference is networking. So make a new friend. You are going to do the stretching exercise with that friend. So find a partner. The two of you know each other. Find someone else. Find a new friend. In the two of you know each other. You know each other. You can't be there. Find a new friend. Okay, with that, let's just take it back. Think you have any questions? I think you have any like.
I think one of them is very. I think because of the.
How about you? Are you ready?
Understand this.
Okay, please, are you ready for the stretching exercise? I'm seeing that somebody is very beautiful. So, which I like this part, why you have to stretch. Please, are we ready for this? Dr. Brown. Dr. Brown. Dr. Brown, you know you're doing it. Please, please explain it. Are we ready? Oh, I don't Okay, so Matt God will show up in one. Okay, please have your attention. Okay, so please, you do answer that.
Hello, everyone. Let's try. Hello, everyone. Let's try.
Each way, both of your arms. Wait.
Okay.
That's what I mean. So I took your name. Did you get? Oh, no,
Let's try. Can we?
I'm not seeing you do the exercise.
Let's do this.
The last one.
That's the last.
The exercise. Each stretch your legs for a very long time.
Black
So,
stars. Yeah.
why
One
is
starts to circulate through my
Yes.
entire body.
blood circulation at the stage?
That.
So knee up, knee down, knee up, knee down. This way, don't make sure your hands touch your Bring the knee all the way up to your stomach area. Knee up, knee all the way. I'm not seeing it too. Thank you very much, Mr. Vincent. I see that you Okay, thank you very much. I hope we are all now widely awake and ready for the last. Okay, let's get start on the last. Thank you.
Let's.
I would start, otherwise I would never start. Mike, how about this? It's not activity background, right? It's something like that. Okay, so someone asked me some more details during the break. Was very good.
In particular, someone asked me some more details of.
I would say something about the power. Um. Yes. Okay, so the idea is to have some algorithm. We will see some algorithm later on, maybe tomorrow. Okay, before going into the data, I want just to refresh this. So we have built some. So this is the secret. I want to say something about the secret that we use to look for the. So you have the registers, there for the registers. There are quantum registers. So this is a quantum bit, which is this one. And this is a classical bit. So this you are 0, analog, and then classic, and then the classical measurement. After you measure, you might have either 0 or 1. These are the real results. These are the percentage out of 1,000 of several variables. So 1,000 ways you build the secret and you measure. You build the secret, you measure. And of course you can find the percentage of 0, 1, first. So it's very difficult to get information about the initial state. There are two variables. That you don't have any information on the page. I don't know why. This is a more complex circuit, but we have already seen something like that. And you see that in some way you have one duplicate like Synapse. So now you can okay. So these are some example of famous algorithms that can be used in quantum computing. One is the factorization algorithm. We know that cryptography is based on many cryptography strategy based on the fact that you have a big number which is in the unlimited number is probably this is a kind of a system. So it's difficult to factorize a large number, but the shell algorithm show that it's possible to do it in a very efficient way. You have a large number. And solve all the functions for the society is going to and the same control that exists and also how we can and quantum resistance. Probably there are basis of stuff. But this is other properties of mathematics. But up to now, what is the situation? It's the part of the numbers that you can factorize with the real quantum computer. So, we will see in the next slide. Okay, so yeah, of course, there is other application, data science, bioinformatics. Although it's simple, it's always difficult to get in and out of a quantum computer. So communication, the be not featured. Sure. Having a lot of data. Probably you should professor and here there is another interesting algorithm which is not particularly interesting, but I mean it's not very advantages, but not really a lot of advantages, but it's nice because we can understand the Robust algorithm. I hope we will be able to make it like this. And then there is one machine learning that will be talking. But then there are other fields more related to chemistry. And these other fields are okay, this is exponential speed increase, finding eigenvalues and other factors. Eigenvalues and other factors are very important. If you have an exponential speed up, indeed, this is very good. So this is a combinatorial problem. You know all these combinatorial problems, but you have to go it's not this problem, but it's a kind of combinatorial problem. So there are some specific cases where this is an exponential speed up, theoretically. Then there is this. Okay, this is some hard physics problem. And then there is this. This was the coverage nature. Incredible how old it is. It's almost 10 years, 2017. The coverage nature, let's say, chemical potential. Quantum computer extend and reach to solve the electronic structure of small bonds. And this is the reason why the powers of particle because the last second, because chemistry is probably the application more reachable part of the quantum computing. Okay. Okay, what is it? The physical realization of how is one of the physical realization of quantum computing? One of the most promising devices are carpet high quantum computing. What does it mean? It means that you have a vacuum chamber, so you remove anything else. And you have ions that are located, suspended in several precise positions. Finally, from the chart, like in the room. Okay. This is a picture of the island. It's a photo. The island. And the photo is probably the mean of the photo. And this is it on this direction and not on the other direction. Okay, so this is not a picture taken by a single photo, but it's a farm of many reasons. Different because you see single atoms, and you see single atoms. That's why this all different ground is very delicate. And imagine another atom from this vacuum, there is not enough vacuum. There is another molecule that bounces on one of these atoms. This delicate state is problem. And one way to implement the quantum computer is take each one of these atoms and to be represented as a qubit. For instance, what which are the parts that correspond to the preparation, control, and measurement? You remember that our state is our quantum computer has to prepare the state, do some control and manipulate the state, and then measure it. Okay, we use an example of this singularity. By the items of atoms, this is the but anyway, so you have a graph state, which is the one state. I don't know why this is always the one state and not the zero. So let's make another choice, but usually this is the one state. This is the zero state, and these are the other electronic states. Okay. So, for instance, if you want the zero and one state which are stable in time. So if one is a zero state, it can stay there for a long time. If it is in a one state, it can stay there for a long time. If it is on this state, it is the case on the one state. Okay, so now I can make some state preparation. That means how to got them since preparation before, like setup or initial starting point. Okay, initialization. How I initialize my qubit? Just by sending lots of flashes to the atoms with this frequency. The one that is resonating from the different zero on this state. This way, if the atoms in the one state, remain in one state. Then it is the one in the zero state, both of them the one state. So after a certain time, you're sure that all the atoms are in one state. Okay, this is the initialization. Then you can have, so you have the atom in the one state. Then you might send other lasers that exist. These lasers are very complicated and they are able to create a superposition between this zero state and the one state. Okay. There is a lot of things behind. I'm trying to figure it out. I'm not people realizing real time. But basically, the control is based on also laser parts, which are tailored in order to satisfy the coming up. Which are disregarded. It's not as part of the game that is prepared to go on. The laser is the Hadamard gate. When you hit this laser, this qubit will go into the position. But then there are more complicated lasers that can also have the whole qubit gate. one have a list that has a CNOT gate and many things. Then there are also some interesting feature that is due to the geometry of this ion drum. If you want to make a CNOT between these two, it's easy because they are close. So you might have a laser that evolves only and mix them together in order to apply CNOT to this. If you want to make a CNOT between this and this, you can move the atoms, get them closer, make the CNOT, and put them back. This is an incredible technology, which is a technology that's moving atoms alone in one chamber to other lasers that are working as very small APs. Ways to lasers. And out of this, you can build what you want, the state you want. And even if this atom goes here, correlated with this, and come back, the wave function will be still correlated. Okay, so the wave function is still there. It's not collapses, it's not changes until you do some measurements. How do you do some measurements? You do some measurements by sending flashes with this energy. So if the atom is in zero, you don't see anything because zero cannot absorb this energy that is not here. Okay? If the atom is in the one state, you absorb and emit again, and you see the emitted line. You say, okay, the wave function now is in one state. If you don't see anything, it's the wave function of that should be in one. So you see, it's very complicated. There is a lot of technology behind that. That's the reason why quantum computers are. I mean, there is a roadmap. Also, IBM has a roadmap, and Google has a roadmap. All these big companies has a roadmap that provides a quantum computer with a certain number of qubits in a certain number of years. Yeah, this is just to say again, initialize, control, and measure. There is not only this way to make quantum computer. Another way is the so-called superconducting qubit. Superconducting qubits. Superconducting qubits are based on the fact that even macroscopic objects, so not objects that are like billion or billion of atoms, I don't know how many objects, but this is a real wire. Small, but it's a real wire. Then in a wire, everything is compact. Also the current, you cannot be any pair, but there is a limit, which is a limit of 1 electron per day, cannot move less than 1 electron. But the intrinsic limit current is found. So, two ways to have current in the conductor, either clockwise or counterclockwise. On two states. Okay. So one state you call 1, and the other you call 2. This is the way that you move, but this is a macroscopic of 2 states, and 2 states in a quantum computer. We got like that. And then there are also 4 other quantum computer built on photons. There is a lot of technologies. Okay?
nuclear steam system, microwave resonators, superconducting currents, up, down, molecular computers.
I think there are about 20 technology. And now, after, let's say, a lot of years, I think the technology is going on and they are selecting somebody for kind of one is also superconductors, business idea.
The one based on photons, the one based on ions, the one based on plasma.
Who is the winner? We will not know if there will be one dominant technology or not. For sure, one very nice goal would be to join in some way this technology with existing silicon technology. That would be a winning point. Because you can in some way integrate better the existing technology and factories, chip factories with this one. Okay, so there are some, this is, I mean, what is the problem of real quantum computer is that they have, well, okay, I think it's fine, that they have noise. What does it mean noise? It means that you can imagine that any information that comes from outside the qubits can indicate the wave function. You can need to bring anything. This is versus other sorts of noise. I mean that the data that you have not exactly the data, so to speak. 80, not precisely, maybe 99%. Then all these errors as soon as you compute somehow. So it's not like a computer which sometimes there's with a certain physics. But there are some algorithms that may be resistant. Some algorithms maybe you can override the computer that 1 out of 100 checking one so the algorithm is not all I think this is finished. I can switch on paper now. So I hope okay. How can I switch on? Thank you. So yeah, I stop sharing. And I can open some. Thank you. So is there any question? So the two ones who have any question.
Very low temperature. But as soon as you have one problem, you want to contact the there's a way to collapse without this is in a very short time. Okay. If they have so the leaders are and then very short. The program is on. Other on the side, the technology the state can be second. I can second. Our base of but the other way is the problem of that is quite slow transfer, for instance, for flying aids, quite slow to move one atom from one side to the other because they have takes time. But it's true that it's something power and quality and the movements they are in so I connect them only different topics. Yes. Well,
Someone asked about network. So that's what is. And then they don't, they are not going to be able to relate, right? So I don't know. My question is. And in another
Okay, but the third question was if I have very short memories. You can analyze the architecture now. Can the classical computer work as a quantum? Okay. So what we can do, and usually done, is the quantum computer a classical computer. And then we might have several different gates, maybe some of them are okay, other general questions? If not, we will proceed. And we will be ready for the next slide. Yeah, I would say something about that. So, one thing that I think strange was that you have something that you very fast but not so much. The value, it's such a part. So the gate that you get the value, I don't know. You can have let's see that this game is very that has the quantum bound. So so one question can be what kinds of conditions we can have for the use of other and we also depend on the demand. Well, this is the same example in almost systems yes. So if we not do the same number of these, okay, of course, we don't have to use it this
And according to which but if you want to do the classical navigation, which is the completely classical calculator, in 3 qubits, and you want to get it around. This is the other and another example is that if you create this
You put one here, three here. One here, three here, zero here. Two here. One here. One here, three here. And here there is here is C plus A and B. C is 0, A and B is A. So here is A. So G was actually the detail is here. Actually, the but that actually is not only replicated. It's bigger. So you can copy something. You can have the okay, this is now the position. Everyone has heard about the position. Can you go back anything? This is the position. You enter the door and you access the start of the gas. So this is a physical element which is kind like the most physically present. In terms of quantum, teleportation means to teleport information. But the second way teleporting, it's quite interesting. So teleportation, it was shown experimentally for the first time in 1997. And there were many experiments. Teleports and information from all parts of the world through some. You see what we are going to teleport. And it is this is not time in 104 kilometers. And it is also done between the Earth and some satellites. Okay. So this is something well established. Okay. So the topic is basically practically is moving at a quantum scale. Even in absence of a quantum computation. So if I have a longer values, I can move a quantum scale. Even 1,000 seconds. But if I don't know that. Okay. Typically, two lines, lines, and it's go. And so, we're together and then allow, and then we have to generate okay. So then is the each one, as you say, this is as one. So the first two was taken by that. The second you can just take it back. But if you even if they are still connected together, what is happening? Okay, let's go to the elements for maybe completed. And one was one of we go to the second place. Look at about the existing. We'll see the dimension. The one deliver one stage for. Then also no condition is one stage. The one stage that has an existing problem solved. And that is the first one stage. And that's not one stage. She has a single copy. Okay. Maybe no one say she should go the future decision. Maybe but I think that has done how far is not comprehensive. She she had a proposal. After a certain time, she one minute of the job. Then she wants to go. And then asked to go, oh, can I have this previous which many times ago? Take it out of the previous. Take it out of the previous, and write that previous, this is kind of the but this is the one of the studies following Genesis connection. And after doing that, magically, the state of Genesis was transferred perfectly in the previous story in the laboratory. Okay. So there is no physical happening. But the question is not because and one of the founding and this is okay, now I have to know the secret is that as and we can see and by hand that this is this is this is the critical sign. Remember, so this is one second. This is Euclid. And this is the system. It was done. This is under the about the treatment. The independent is using the computer. And the law has provided the it is the so the data provided are classified. This is okay. This is very clear. This is the separation line. This is Alice line. This is Bob. Okay. So you have Alice line. Alice has one half of the target space Bob and another state. Bob has is just a bit of how doesn't the bridge. And what is this line? This line is the communication that Alice did in Bob by phone. Okay, please apply X, please apply that, please don't do anything. The message of the and for mention this started page with his own community. And for his management. So now what we have several steps. So this is the one. And here we we have also let's go step by step. So who is it? That it is really state. Okay. The state to be the box that it is side. And side is the column from the room. So society is the combination of side and repeated. So I want to mention this. So side side is this one because it's a shadow between the four. And one is like a small. But this is by this. But I know by this. This is correct. Sì, potete fare anche. Let them play this. Where can you play this? Okay. You can the word on the computer. The decision is varied between this agreement and this agreement. Okay. But the first agreement, this agreement, the difference of pay, and then on the computer. Meaning that the control is the control. And the target is the poi da le si sono preparate dentro now control is one, so in the direction. This is me. One, five. One is zero. Plus is zero. One. One. And then from here to here, it's just a matter of changing the location. Changing the position, this way, this way. So my God, and then trying to do this. And the last one separated on the left hand because this is a cube that belongs to. Which is a combination of 0 and 1. Now, what we're doing is if we take a minute of error computer. This is. It's a remember, everything is she is managing away from all these differences, which is within a combination of the variables. When we manage all the equation is a zero, then the infrastructure allows only one. You shouldn't. Okay. So it is matter just how energy.
One. Wow. Okay. So now I'm going to one. This is that is one and as method. All these are experience. And only this one repeating. So all has it is three. The cubic, which is like that. Which is similar to the one that Alice had. Very similar. Okay. It's not exactly the same, or it's the same one. It's the type cubic. What if you do the two? This is the same as the analytic. The analysis. What if you do? You really a small disease, which you have to apply. Those kind of diseases. But is a two cubit. This is one cubit, huh? This is just one cubit. This is not the cubit of okay, you wanted to say like no. The X gate. Correct. The X gate. The X gate is just changing. So Alice will make the let for the because you apply the X gate to the gate and reach. Well, like the X gate and transform this gate into one. Okay. So of course, you can remind us of the down and 0, you will have to try this. If the outcome was 0, 0, which means you have to try. This is a pretty analysis one. So don't apply anything. So you have no possibility if you have 1, 0, what would have been? If you have 1, 0, you have this one. Which is made as one is then
You have this one. So it is both extended and with the cross behind on the. Now, why is it using imaginary model? So you have private X and invert the coefficient, and then you have a private. So this is basically what is described in this last part. Okay, so in the last part, there are so many options. The last part, in the last part here, very geometrized. You see that Bob has just done a qubit that was, I mean, was just half of the vegetable. But now he obtained a qubit from a system. What would be the mentioning a hundred lives. What is the life? I mean, for what? You estimate the measurements and immediately thought as something finished. Okay. This is not what the life. But then there's more community kind of game as a flight level. So without that, software assumptions, and you don't know which one of the station is. It's anyway, the probability, if you look at this, what doesn't know which station it is, and what is it? If the probability of getting 0 and 1, all the stations taken together, and anyway, what is the probability of getting 0 and 1? I mean, it doesn't depend on so if it is this case, it's really more probable than 1, but it could be another station is more probable than 0. So, can anything useful without knowing from analysis what to do on. Start. What is too far? Okay. What is too far? Right. Sorry? Yeah. I agree. Okay. So let's have it.
So, in some way, you say the teleportation is to make a measurement. The measurement destroy the state. It's not that destroy the state, it collapses the state into zero. Okay. But this collapse is partial because it only occurs on the cubital, the cubical on the left. So is the wave function, is the fact that the wave function that the last lattice is collapses, not the one that's lost. Well, this is very important. Okay. So this measurement in some way have an effect, direct effect on so this collapse influences the cubical in some way. Okay. But the cubical is still alive in some way. It's not alive. It's still superficial on very wide. It's not just 0.1. So, and one next, what you say is, yeah, it's true that you can explore and you can teleport. So we have some other questions? This kind of function for the time bitwise. So when the computer will be these things and then the system function doesn't function that's called another bit of course you can align this function in the bits for analysis. So what does it mean? We have already seen such a case where that was the addition of this. Okay, that was the but in general, this can be any functional analysis. It's not necessarily any functional analysis. And not necessarily. The indicator that we have seen that it was 1 plus x. But this can be also function of x. Whatever. I mean, that has not very. It's 0. It's 0, 1. It's 1, 0, 1. So the second number of this function. This is 4 factor. So, so the output. So this would be y. X equal to 0. And the y negation is x. Okay, so this function can be described by the unitary operator. So you have this is operator unitary. Use square. If you apply 2 times its operation, what do you get? U. And I will combine x and y minus. It's one, because it's already one. Is x, then it's one plus x, again plus x. This is x1. So that means that the new square is equal to the density. Okay. So if we move this is equal to the minus 1, this is a unitary. Okay, so we are seeing that somebody extend this consider that it's not of just one case of the minus possible cases. This depends on this function we will use tomorrow. Unfortunately, we haven't gathered in the last section. Maybe ask also time we are a facilitator come with us, ask questions that we have about everything and we will try to answer. Thank you.
We pray.
The past. You take them there, yes, so if I can. Well, so I think tomorrow, yes, tomorrow you have that that's when the class, that you can hear before take your breakfast. Breakfast stay yeah, I'm not able to say it. More used to
Relax, relax. I see.